Imagine, just for a moment, that you're floating in the vast emptiness of space, weightless, silent, surrounded by an infinity that stretches in every direction. Earth is just a pale blue speck behind you, shrinking with every passing second. Ahead lies everything: the moon, the planets, the distant stars, the mysteries of black holes, and the very edge of the observable universe. This is where we're going. Welcome to Quiet Universe, where we leave behind the familiar and step into the unknown. Since the beginning of time, we've looked up at the night sky and wondered what's out there. The stars have been storytellers, guiding travelers across oceans, inspiring myths and legends, and teasing us with the possibility of worlds beyond our own. But today, we're not just looking up. We're going. This journey will take us from the ground beneath our feet to the farthest reaches of the cosmos, a trip fueled by curiosity, science, and a little bit of imagination. Space travel has always been more than just technology and rockets. It's about us, about human beings refusing to be confined to one place, about our need to explore, to reach beyond what we know. It started with stories, science fiction dreaming of moon landings and interstellar adventures. Then came the reality: rockets piercing the sky, footsteps on the moon, rovers rolling across Mars. And yet, we've barely scratched the surface. So, what happens when we push further? What lies beyond the thin blue line of our atmosphere, past the satellites and space stations, past the rocky surfaces of our planetary neighbors, past the great gas giants and their frozen moons? What do we find when we go beyond our solar system, past our galaxy, into the great cosmic web that ties the universe together? And if we ever reach the edge, what's waiting for us there? This is a journey both theoretical and grounded in science, a mix of what we know and what we can only imagine. We'll move outward step by step, traveling from Earth to the edge of everything, encountering celestial wonders along the way. So, if you've ever stared up at the night sky and felt the weight of the universe pressing down, if you've ever wondered what's beyond the stars, if you've ever dreamed of setting foot on another world, then this is for you. Strap in, because we're leaving Earth behind. There's something both terrifying and exhilarating about looking up at the night sky and realizing that, despite everything we know, despite all the equations and measurements and telescopes and satellites, space remains a place of almost pure mystery. It stretches out in all directions, vast and indifferent, an expanse so immense that our own planet, our entire solar system even, barely registers as a speck in its depths. And yet, for as long as humans have existed, we've been staring up at it, wondering, imagining, and eventually trying to reach it. The stars have called to us for centuries, not just as distant pinpricks of light, but as destinations, as places we might one day set foot upon, as realms where the impossible might become reality. The idea of leaving Earth and traveling deeper and deeper into space is more than just a thought experiment or the premise of a sci-fi novel. It is a journey shaped by history, by raw ambition, by an unrelenting human need to push boundaries, to defy limits, to go beyond. The first time we broke free from Earth's grasp, it was with trembling rockets, primitive by today's standards, yet revolutionary in their time. Sputnik, a small metal sphere, was the first to slip the bonds of our atmosphere, followed by brave explorers who risked everything to venture beyond. The moon, once unreachable, became a footprint in the dust. And now, decades later, as we stand on the edge of an era where Mars colonization is no longer science fiction, where private companies send tourists to the fringes of space, where telescopes capture galaxies as they were billions of years ago, it feels as though the universe has never been closer. But for all our progress, we remain confined to our little corner of the cosmos. No human has gone beyond the moon. Probes have drifted outward, whispering back secrets of the planets, of icy moons and swirling storms and landscapes untouched for eons, but we ourselves remain tethered to this world. The dream, however, has never died. If anything, it has only grown. The questions that once seemed distant, hypothetical, are now pressing. What lies beyond? How far can we go? What would it feel like to drift through interstellar space, where even the nearest star is years away? This journey is not just about imagining a spaceship blasting off from Earth and charting a course into the unknown. It's about what we would truly see, feel, and experience along the way. From the moment we leave Earth's surface, everything changes. The sky fades from blue to black, the air disappears, the comforting pull of gravity vanishes. Familiar landscapes become dots below us, shrinking into a marble of swirling blues and whites, beautiful and fragile. In orbit, Earth is both impossibly close and impossibly far, home and yet a place already out of reach. As we push further, past the satellites that circle like tiny sentinels, past the space stations and debris left behind by decades of exploration, the world we knew recedes. The moon appears, a stark and silent witness to our departure, a place that has known human footsteps yet remains eerily still, untouched by the winds and weather that shape Earth. Beyond the moon, the solar system begins to unfold in ways few ever truly consider. It is not just an empty void, but a place teeming with worlds. Some familiar, some utterly alien. Mars, with its rust-colored sands and whisper-thin air, a place we might one day call home. The gas giants, with their swirling tempests, their moons locked in frozen mystery. Asteroids drifting like ancient relics, remnants of a time before planets even formed. And the sun, always the sun, its presence undeniable even as we drift further from its warmth, from the light that has sustained us for so long. But the real journey, the one that stretches into the unknown, begins when the planets fall behind, when the sun becomes just another star among billions. Deep space is a concept that most struggle to comprehend because it is so far removed from anything we know. It is not merely distance, but a profound and unsettling isolation. In deep space, there is no horizon, no ground beneath your feet, no up or down, just an endless, incomprehensible expanse. It is a place where time itself feels distorted, where light takes years, centuries, millennia to travel, where even the fastest spacecraft ever built would take lifetimes to reach the nearest star. And yet, it is here that the universe truly begins to reveal itself. It is here that we come face to face with the incomprehensible scale of reality, where galaxies stretch out in an infinite web, where black holes lurk in the darkness, where entire civilizations, if they exist, might rise and fall unnoticed. It is a journey that forces us to confront our own insignificance, to question what it means to be human in a universe that does not care whether we exist or not. And yet, it is precisely because of that insignificance that we keep looking outward, that we keep searching. Because the farther we go, the more we understand that space is not empty. It is alive with possibilities, with wonders waiting to be discovered, with stories yet to be told. So we embark on this journey not just out of curiosity, not just to see what lies beyond, but because that is what we have always done. Because from the moment our ancestors first looked up at the sky, we have known, deep down, that we were never meant to stay in one place forever. 1. Leaving Earth. The moment of leaving Earth is not as simple as just pointing a rocket upward and hitting the launch button. It's a slow, almost reluctant escape from a world that has spent billions of years shaping everything we know. The atmosphere is not just an invisible layer of gases. It's a protective cocoon, a shield that keeps everything in balance, allowing life to exist. But the same atmosphere that nurtures and protects also resists anything trying to leave. It grips tightly, demanding immense force, fire, and precision to break free from it. At the surface, standing on solid ground, it's easy to forget that we are submerged at the bottom of a massive ocean of air, one that grows thinner with altitude. The lowest layer, the troposphere, is where everything familiar happens, where the air is thick enough to breathe, where clouds form, where storms rage, where birds fly. It stretches only a few miles upward, yet it holds nearly all the weather, all the life-supporting oxygen, all the moisture that fuels the cycles of nature. A rocket lifting off from the ground first has to push through this dense, turbulent region, where drag is at its highest, where every bit of thrust is fought against by the sheer weight of the atmosphere pressing down. As the ascent continues, the air thins, and the world below starts to look different. The blue fades, clouds become distant patterns instead of towering masses, and the wind that once howled past the rocket's surface begins to fall silent. The stratosphere is next, a realm of smooth, stable air, far above the chaos of weather systems. Here, the ozone layer silently does its work, absorbing ultraviolet radiation, protecting everything below from an otherwise deadly bombardment. In this place, jet planes cruise, their pilots knowing that even a small mistake at these heights could mean a rapid, irreversible plunge back to Earth. It is also the home of the highest weather balloons, fragile instruments that rise until the air becomes too thin to support them, their rubber stretched to the breaking point before they burst and drift back down. Higher still is the mesosphere, a cold, mysterious layer where temperatures plummet and strange phenomena occur. This is where meteors burn up, where streaks of light flash across the sky as tiny space rocks, traveling at incredible speeds, slam into the atmosphere and disintegrate in fiery displays. It's an unforgiving place. Too high for aircraft, too low for satellites, a region barely explored, yet vital in its role. The air is so thin that even though the pressure is only a fraction of what it is on the ground, it still drags against anything trying to pass through. Then comes the thermosphere, a place where the very definition of temperature becomes meaningless. Here, the sun's radiation is intense, energizing the sparse particles of gas until they move at incredible speeds. If you were standing in this layer, you might expect to feel extreme heat, but there is so little air that there is nothing to transfer the warmth. It is here that the auroras dance, where the charged particles from the sun slam into Earth's magnetic field, painting the sky in shifting greens and reds and purples. The International Space Station orbits at this altitude, just barely clinging to the edge of space, its speed keeping it in a delicate balance between falling and escaping. Beyond this is the exosphere, where Earth's influence starts to fade. Air molecules drift apart until they are so sparse that the line between atmosphere and space becomes more of a transition than a boundary. It is here that some of the fastest-moving particles on Earth, energized by the sun, finally break free and drift off into the void. The higher you go, the quieter it becomes, until there is nothing left but silence. The pull of gravity still exists, but there is no air to hold you down, no atmosphere to fight against. At last, after so much resistance, after pushing through layer after layer of thinning gases, a force is trying to pull you back. You are no longer within Earth's grasp. The planet below is no longer a place you walk upon, but something distant, something seen from above. It is no longer the world, but a world, one among many. The blue fades into black, the air into emptiness, and space, for the first time, is not something imagined or observed from a telescope, but something real, something all-encompassing. The atmosphere is behind you now, the last physical connection to the place where everything you have ever known has existed. And ahead lies the unknown. Kármán line, the boundary of space, 100 kilometers up. There comes a point in the ascent where everything changes, not suddenly, but unmistakably. The engines are still roaring, the Earth is still pulling, but the air has given up its grip, and the sky is no longer blue. This is the Kármán line, an invisible but significant threshold, the place where space officially begins. Though the universe itself doesn't acknowledge such boundaries. It is not a physical wall, not some sudden barrier that one passes through like stepping from one room to another, but a calculated altitude, about 100 kilometers above sea level, where the atmosphere becomes too thin to support conventional flight. Below this, wings and aerodynamics still matter. Above it, only velocity and orbital mechanics rule. For those making the journey, reaching this altitude is a moment that is both triumphant and humbling. From here, Earth no longer looks like a world that stretches endlessly in every direction, but instead becomes something finite, something with edges. The horizon curves unmistakably, and the thin haze of atmosphere clings to the planet like a fragile shell. Everything once taken for granted. The breathable air, the comforting blue sky, the weight of gravity pressing down, is now something left behind. In every direction beyond the planet's edge, there is nothing but the deep, endless black of space, not dark like a night on Earth, but absolute, empty, consuming. The Kármán line is not just a scientific definition. It is a symbolic divide, the point where a human is no longer just flying but has truly left the planet. Astronauts who have crossed it describe an overwhelming shift in perspective, the realization that they are no longer part of Earth in the way they once were. There is no up or down anymore, only movement, only trajectory. The world below is silent, untouchable, spinning beneath them with no awareness that they have left. The air that once resisted every motion is now gone, and in its place is the stark, unforgiving void where everything must be carried. Oxygen, warmth, protection, because space provides nothing but an endless vacuum. For those watching from below, a rocket passing this altitude is just a distant light, a streak that vanishes into the sky. But for those aboard, it is the moment they leave behind everything familiar. No more weather, no more sound, no more friction against a wing or a hull. Just inertia, just physics, just the fragile existence of a human in a place never meant for them. The Kármán line is a number, a definition, a guideline for where space begins, but in reality, it is something more. It is the last breath of Earth's atmosphere, the final whisper of air before the great silence. It is the point where a journey stops being a climb and becomes an escape. Gravity and escape velocity. Why rockets need so much energy. The moment a rocket is on the launch pad, towering over everything, fueled and waiting, it is not just facing the sky. It is facing an invisible force that has held everything down since the beginning of time. Gravity is not something that can be switched off or negotiated with. It is relentless, pulling at everything with the same quiet persistence, dragging objects toward the center of the Earth with a grip that never loosens. And the only way to break free from it is with sheer, overwhelming force. That is why rockets are not sleek, effortless machines that simply glide into space. They are fire and chaos, explosions controlled just enough to push against a force that does not want to let go. Escape velocity is a cruel, non-negotiable number. To leave Earth behind entirely, to ensure that gravity does not eventually pull you back down, an object must reach about 11.2 kilometers per second, over 40,000 kilometers per hour. It is an absurd speed, one that no plane, no car, nothing on the surface of the planet ever comes close to reaching. This is why rockets are not just vehicles. They are controlled detonations, engines designed to burn through fuel at an almost ridiculous rate, shedding weight, discarding empty fuel tanks, doing everything possible to reach the one speed that means freedom. Everything we see around us, everything that is not actively being held up, is at the mercy of gravity. A ball thrown into the air slows, pauses for the briefest moment, then comes back down. A plane can cut through the air, ride on lift, but it will always need an atmosphere to stay aloft. Even objects in orbit, satellites, the International Space Station, are not truly free from gravity. They are simply falling in a way that never brings them back to Earth. The only way to escape completely, to go beyond the reach of this unseen hand, is to be fast enough that gravity can never catch up. That speed comes at a cost. Rockets have to carry an enormous amount of fuel, not just to move forward, but to fight against the constant pull of Earth. Every kilogram of weight demands more energy, and every bit of energy spent means more fuel is needed. But the fuel itself adds weight, which then requires even more fuel to carry it. It is an endless struggle, a battle of physics where efficiency barely exists, where nearly all the energy is used just to push through those first few minutes of resistance. Once a rocket finally reaches space, it does not need to keep firing to stay there. Without air, without friction, motion simply continues. But getting there, escaping the tight grip of Earth, is the hardest part. That is why launches are violent, deafening, filled with fire and smoke, shaking the ground beneath them as engines push with millions of pounds of force against something that does not want to let them go. It is not just about reaching a destination. It is about overcoming something that has never let anything escape without a fight. And in that moment, as a rocket finally breaks free, leaving behind the weight of the world, it is not just a machine that has succeeded. It is human determination, defying the force that has ruled for billions of years, if only for a moment. Spacecraft and rockets. The journey into space has never been easy, and the machines that have carried humans and cargo beyond Earth are proof of that. They are not just vehicles. They are carefully engineered lifelines, designed to survive the most hostile conditions imaginable. Every spacecraft, every rocket, has been built with one purpose in mind: to defy gravity, survive the vacuum, and either return safely or drift endlessly into the unknown. Some have been towering monuments to raw power, like the Saturn V, the behemoth that took humanity to the moon, while others, like the International Space Station modules, are more like tiny islands of habitability in a sea of nothingness. Then there are those still being developed, like Starship, which promises to take people farther than ever before, and Orion, built for deep space exploration, meant to push the boundaries of where humans can survive. Saturn V was a monster. It was not just a rocket. It was a controlled explosion larger than anything ever built for space travel. Standing taller than the Statue of Liberty and burning through millions of liters of fuel in mere minutes. It was designed with one purpose: to leave Earth behind with enough speed and force to take people all the way to the moon. No rocket before or since has matched its sheer power, and every time it launched, the ground shook, the air cracked apart with sound, and an entire nation held its breath. It was not sleek, not elegant. It was a brute force solution to one of the biggest challenges in history, and it worked. It carried the Apollo missions beyond Earth, through the void, and to the surface of another world, proving that, despite everything working against it, human ingenuity could overpower nature itself. But the journey did not stop there. Space is not just a destination. It is an entire frontier, and exploration does not end with flags planted in the dust. The International Space Station is the closest thing humanity has to a permanent home beyond Earth, a patchwork of modules built by different countries, all assembled in orbit like a high-tech jigsaw puzzle. It is not large, not compared to the vastness it floats in, but it is enough, just enough, to keep a handful of humans alive, working, and watching the Earth spin beneath them. Every module, every cramped living space, every window offering a view of the planet below, is a reminder that space is not welcoming. It is cold, silent, and indifferent, and without these metal shells, no human would last more than a few seconds. The future of space travel, however, is being written now. Starship is meant to be the next step, not just another rocket, but a fully reusable system, capable of carrying people not just to orbit, but to Mars and beyond. If it works, if it becomes what it promises to be, it will change everything, making space travel routine, affordable, and no longer just the domain of governments. And then there is Orion, built for deep space, not just short trips to orbit, but long journeys, pushing the limits of human endurance and technology alike. It is designed to take people back to the moon, maybe one day to Mars, a vessel for those willing to leave Earth behind for something more. Each spacecraft, each rocket, tells a story of struggle, of pushing back against the impossible. They are metal, fuel, and fire, but they are also hope, a testament to the fact that humanity has never been content with staying where it is. They are our way of reaching beyond, of seeing what waits in the darkness, of proving that, despite everything, despite the forces working against us, we are meant to go farther. And maybe, just maybe, these machines will not just be the way we leave Earth, but the first steps toward never having to come back. The feeling of zero gravity. What happens to the human body? Floating in zero gravity is not the effortless, dreamlike experience people imagine when they see astronauts gracefully drifting through the International Space Station. It is not as simple as just being weightless. It is a complete rewriting of everything the body has ever known. From the moment you are born, gravity is a constant, an unspoken rule that governs every movement, every step, every breath. Your muscles push against it, your bones grow strong under its pull, your inner ear relies on it to tell you which way is up and which is down. But in space, all of that is gone. The body is suddenly untethered, left to float with nothing pulling it in any direction, and that shift is not always as pleasant as it looks. At first, the feeling is strange, almost unreal, like your body has somehow detached from itself. Your arms drift upwards when you are not paying attention, your legs no longer have a reason to hold you up, and suddenly, movement itself becomes a problem. Pushing off a surface too hard sends you tumbling. Reaching for something to stop yourself turns into a slow, clumsy spin, and even the smallest motion has unexpected consequences. It is not just a matter of learning to move differently. It is learning to exist in a completely different way. There is no sense of up or down, no natural way to orient yourself, and that is where the real problems start. The inner ear, the part of the body responsible for balance, does not take kindly to this sudden betrayal of gravity. It expects the familiar pull, the reliable sense of direction, and without it, things go wrong fast. Many astronauts experience space sickness, a strange, uncomfortable mix of dizziness, nausea, and disorientation that makes the first few days miserable. The body struggles to adjust, the brain tries to make sense of conflicting signals, and even simple tasks become exhausting. Some get over it quickly, others take longer, but for most, the first experience of weightlessness is far less magical than they had imagined. Then there are the deeper, longer-lasting effects. Without gravity constantly pulling blood downward, fluid starts shifting upwards, pooling in the upper body and making faces look puffier, noses feel permanently stuffed, and heads feel heavier than they should. At the same time, the lower body starts losing muscle mass because there is no need for strong legs when you are not standing. The bones begin to weaken, slowly losing density, a process that would be barely noticeable on Earth, but becomes a serious problem after months in space. The heart, used to pumping against gravity, starts working differently, adapting to the new environment in ways that are not always beneficial once a person returns to Earth. Even sleep is strange in zero gravity. There is no lying down, no comfortable position, just the feeling of floating, of being held in place by a sleeping bag strapped to a wall so you do not drift away in the middle of the night. Dreams feel different. The body never quite relaxes the way it does on Earth, and waking up means reorienting yourself all over again. Food does not settle the same way in the stomach. Muscles need constant exercise to avoid wasting away, and every part of daily life has to be relearned. But despite all the discomfort, all the confusion, there is something undeniably freeing about it. There is no effort required to move, no strain, just the simple, strange reality of existing in a place where gravity has no hold. It is a reminder that the human body is not designed for space, but at the same time, it shows that with enough time, it can adapt. And for those who experience it long enough, there comes a moment where floating no longer feels unnatural, where movement becomes instinctive, and where weightlessness is not just an obstacle, but a new way of living. 2. Low Earth orbit and space infrastructure. The International Space Station. Low Earth orbit is the first real stop after leaving the grip of Earth, a chaotic, crowded zone where humanity has left its mark in the form of satellites, space stations, and a growing cloud of debris that drifts endlessly with nowhere else to go. It is not quite the vast emptiness of deep space, not yet the serene, lonely stretch of the cosmos where nothing familiar remains. Instead, it is a space buzzing with movement, with the hum of human presence, a thin layer of technology clinging to the planet like an artificial exosphere. Everything in this region is moving at unimaginable speeds, streaking around Earth at thousands of kilometers per hour, locked in a delicate balance between momentum and gravity. It is a precarious existence. One miscalculation, one collision, and something as small as a screw becomes a bullet capable of ripping through solid metal. And yet, for now, it is the closest thing humanity has to a true foothold in space. The International Space Station is the heart of it all, a fragile metal outpost constantly falling around the planet, a place where humans have lived continuously for decades despite the fact that it was never designed for permanence. It is not a sleek, futuristic city in the stars, but a patchwork of modules, each added over time, each serving a specific purpose, all of it held together by engineering, ingenuity, and the sheer will to keep it running. Inside, it is both impossibly advanced and shockingly mundane. A place where cutting-edge experiments on physics and biology happen just meters away from astronauts struggling with the simple challenge of eating without making a mess. Floating through the narrow corridors feels more like crawling through an oversized air duct than stepping into a grand space station. And yet this is where some of the most important research for humanity's future in space is taking place. The experiments here are not just about curiosity, they are about survival. Every study on how microgravity affects bones, muscles, and the cardiovascular system is a step toward figuring out how to send people further to keep them healthy on the long journeys to Mars and beyond. The plants grown in tiny, artificial gardens under pink LED lights are not just for show. They are a test run for future colonies where Earth's resources will not be an option. Even the fire experiments, watching how flames behave without gravity pulling them in one direction, are more than just scientific play. They are necessary for understanding how to prevent or fight a disaster in space. The station itself is both a laboratory and a home, a place where astronauts wake up to the sight of Earth spinning below them, eat rehydrated meals from plastic pouches, exercise to keep their bodies from deteriorating, and then go to work running the countless experiments that will determine the future of human spaceflight. But the ISS is aging, its systems wearing down, and plans for the future are uncertain. Eventually, it will be replaced, maybe by commercial space stations, maybe by a new international project, or maybe by nothing at all if priorities shift. Private companies are already testing their own space habitats, eyeing the possibility of turning low Earth orbit into a place not just for government-funded missions, but for industry, tourism, and long-term human presence. The idea of hotels in orbit, research stations owned by corporations, or manufacturing facilities building products that can only be created in microgravity is no longer just science fiction. It is a plan that is slowly, awkwardly, moving toward reality. Yet despite all the ambition, all the research, and all the technological advancements, living in space is still an ordeal. Every breath of air is manufactured, every drop of water is recycled, and the station depends on constant shipments from Earth to stay operational. It is a fragile, temporary existence, a reminder that humanity is still taking its first steps beyond its home planet. The ISS, and everything in low Earth orbit, is proof of what is possible, but it is also a stark demonstration of how far there is left to go. For now, it is a place to learn, to adapt, to test the limits of human endurance and technology. But it is not the final destination. It is just the beginning. Satellites and space junk. Orbit is not empty. It may seem like a vast, endless expanse, but in reality, it is cluttered with the silent machinery of human civilization. Satellites, in their many shapes and purposes, drift tirelessly around the planet, providing the invisible threads that hold together modern life. Some are tiny, no larger than a shoebox, flung into space in clusters to form massive constellations that beam internet signals to the most remote corners of the world. Others are massive, hulking machines the size of buses, packed with sensors and antennas, tirelessly relaying television broadcasts, military intelligence, weather predictions, and scientific data. Without these orbiting sentinels, everything from Google Maps to global banking to emergency response systems would begin to unravel. The world below depends on a delicate, unseen web of technology that most people never think about, never see, and yet it shapes every moment of their lives. Some of these machines are watching the Earth with unsettling precision, capturing high-resolution images that can read the license plate on a car from hundreds of kilometers above. Others listen to signals, intercepting communications, mapping military movements, tracking changes in the atmosphere, or scanning the oceans for submarines lurking beneath the waves. Surveillance satellites drift in their silent orbits, unseen and unheard, but they are always watching. Every major nation has them, each trying to outmaneuver the others, a silent game of technological chess played across the heavens. Some satellites, like the GPS network, exist to serve everyone, guiding planes, ships, and even casual pedestrians looking for the fastest route home. Others exist solely for war, communication hubs designed to keep militaries connected, guiding missiles with pinpoint accuracy, or ensuring that should everything go wrong, a nation's leaders can still give the final, irreversible order. But for every active satellite, there are countless others that have reached the end of their operational lives, tumbling uselessly through space. Dead husks of old technology, abandoned after they served their purpose, now drifting aimlessly, waiting for the moment when they will either be pulled down by gravity and burn up in the atmosphere or collide with something else and shatter into thousands of pieces. And those shattered fragments are a growing threat, an expanding cloud of debris that moves faster than bullets, turning orbit into an increasingly dangerous place. A single stray bolt, a piece of paint chipped off an old spacecraft, a fragment from a long-forgotten mission. Each one a potential disaster waiting to happen. Collisions do not just create more junk, they create chain reactions. One destroyed satellite sends out a spray of high-speed shrapnel, which then collides with something else, and then something else, and soon, a once useful orbit is nothing more than a death zone, filled with debris too small to track, but large enough to destroy anything that gets in its way. The idea of cleaning up space junk is not new, but the solutions are complicated. Some propose nets that could catch debris and drag it down to burn in the atmosphere. Others suggest harpoons or robotic arms to remove the largest and most dangerous pieces, while some believe that a laser system could nudge stray objects out of the way before they cause damage. But all of these ideas face the same fundamental problem. Space junk is not just random trash. Much of it is old satellites, discarded rocket stages, and classified military technology, and no country wants another nation interfering with their defunct machines. Cleaning up orbit is not just an engineering challenge. It is a political one, a battlefield of suspicion and control where every piece of junk might still have strategic value. Yet, despite the growing risks, humans continue to send more and more satellites into space, launching them by the thousands in the hope of blanketing the planet in internet coverage, improving climate monitoring, or creating new forms of space-based security. Every launch makes orbit more crowded. Every collision increases the danger, and yet there is no turning back. The future depends on these satellites, on the invisible infrastructure they provide, on the data they collect and transmit. The problem is that the future also depends on space remaining a place where new missions can still be launched, where new technologies can still operate, where humans can still go. And if the debris problem spirals out of control, if the collisions become too frequent, then orbit itself could become unusable, trapping humanity on the ground, cut off from the very systems it once relied on, left to watch as the sky fills with the wreckage of its own ambition. Space tourism and space hotels. There was a time when space was only for astronauts, a distant, unreachable frontier where only the most highly trained individuals could go, riding atop rockets designed not for comfort, but for survival. Now, however, the idea of regular people leaving Earth, even if only for a few minutes, is no longer a fantasy. Wealthy tourists are already paying millions for the privilege of floating weightless above the planet, gazing down at the curve of the Earth through thick glass windows, while the rest of humanity remains trapped under the blue sky. Companies like Blue Origin and Virgin Galactic have turned spaceflight into something closer to an amusement park ride, brief but exhilarating, designed not for discovery or scientific progress, but for the experience itself. The feeling of stepping beyond the world, even if only for a moment. These suborbital trips, lasting mere minutes, offer a glimpse of the vastness beyond, a teasing reminder of how small and fragile everything on Earth really is. But for those with even greater ambitions and even deeper pockets, there are other possibilities. SpaceX, a company that began as a wild dream and is now the dominant force in commercial spaceflight, has much larger plans. It is not enough to merely kiss the edge of space and fall back down. True tourism, real exploration, means staying longer, going farther, making space a place where people can actually live, even if temporarily. The goal is not just trips for billionaires, but something more sustainable. Hotels in orbit, lunar vacations, perhaps one day even a permanent settlement on Mars. The International Space Station, once a place reserved only for scientists and astronauts, has already hosted a handful of ultra-wealthy visitors. But the process has been expensive, complicated, and entirely dependent on government approval. The future promises something different. Private stations, luxury accommodations floating above Earth, rooms with the best view imaginable, where the wealthy can sip champagne while watching the sunrise over the curved horizon 16 times a day. Of course, the reality of space hotels is far from simple. Space is not a place built for human comfort. There is no gravity to keep things in place, no fresh air to breathe, no running water, No easy way to deal with something as basic as sleeping without drifting away or eating without food floating off the plate. The systems needed to keep humans alive are complex, delicate, and expensive, and the idea of turning orbit into a vacation spot requires not only engineering solutions, but a complete rethinking of what it means to relax and enjoy oneself. The challenges are enormous, but so is the market. The first space tourists were willing to spend tens of millions for a short stay. If costs can be lowered, if access can be expanded, the demand will only grow. Yet there is an unease that comes with the commercialization of space. The same companies that promise to make spaceflight accessible are, for now, only making it accessible to the ultra-rich. The first people to stay in space hotels will not be ordinary travelers, but billionaires, celebrities, and corporate executives. And as these privileged few float above the planet, watching the storms swirl over the oceans and the city lights flicker in the darkness, there is an unavoidable contrast. Down below, on the very world they are escaping, billions remain struggling, unable to afford even a plane ticket, let alone a rocket ride. Space tourism, at least in its early days, is not about opening up the cosmos to humanity. It is about the wealthiest individuals indulging in a new and expensive form of entertainment. But even with all its excess and inequality, there is something undeniably significant about the fact that people, any people at all, are beginning to move beyond Earth in a way that is not purely scientific or governmental. Space is no longer just for astronauts, no longer just a domain of national pride and scientific research. It is slowly, inevitably, becoming a part of human culture, a place where people might one day go for a honeymoon, a business retreat, a weekend getaway. What starts as a playground for the rich could, in time, become something more. Today, space hotels are a fantasy, an indulgence for those who can afford them. But so was air travel once. The first airplanes were dangerous, expensive, and reserved for the wealthy. Now, they are part of daily life. Perhaps space will follow the same trajectory, and one day, the idea of leaving Earth for a short stay among the stars will feel as ordinary as boarding a flight to another country. It will take time, decades, maybe centuries, but humans have never been content to stay in one place. The first step is taken by the few, but in time, the rest always follow. Space elevators and theoretical launch systems. There's something almost absurd about the way humans leave Earth. Strapping themselves to a controlled explosion, blasting upward through an atmosphere that fights them every step of the way, burning through enormous amounts of fuel just to break free of the planet's pull. It's a process that is as brutal as it is expensive. Every launch is a precise, high-stakes event, with billions of dollars and years of engineering hanging in the balance. Yet, for all its drama, it is deeply inefficient, a method born out of necessity rather than elegance. If humanity is ever to move beyond this stage, if space is to become truly accessible, something better will be needed. Something that doesn't rely on single-use rockets or staggering amounts of fuel. Something like a space elevator. The idea is deceptively simple. Rather than launching into orbit with rockets, why not just build a structure that reaches all the way from the surface of the Earth to space itself? A tether stretching tens of thousands of kilometers into the sky, held taut by centrifugal force, with an elevator capable of carrying cargo and people into orbit with far less energy than a traditional rocket. No deafening explosions, no staging separations, no burning through millions of dollars in minutes. Just a slow, steady climb, like an escalator to the stars. In theory, it is the most efficient way imaginable to reach space, a method that could drastically reduce costs and open up the cosmos to more than just astronauts and billionaires. But in practice, it is almost impossibly difficult. The materials needed to build a tether that long, strong enough to support itself against the pull of Earth's gravity while also resisting the stress of the planet's rotation do not yet exist. Carbon nanotubes, graphene, and other futuristic materials are often brought up as possibilities, but none have yet been produced on a scale that would make such a structure feasible. Even if the material problem could be solved, there would still be the challenge of assembling it. Constructing something that stretches from the ground to geostationary orbit, keeping it stable in the face of weather, orbital debris, and the constant movement of the planet itself. Theoretically possible, perhaps, but realistically, still far beyond current technology. And yet, even if a true space elevator is out of reach for now, other alternatives exist. Some have imagined massive electromagnetic railguns, known as mass drivers, built into mountains, using electromagnetic force to propel payloads into orbit without the need for chemical rockets. Others have suggested enormous spinning tethers in orbit, capable of catching spacecraft and slinging them outward, like a cosmic slingshot that could reduce the fuel required for interplanetary travel. There is even the dream of a launch loop, an enormous circulating cable running at extreme speeds, capable of lifting payloads into space using pure kinetic energy. These ideas, wild as they may seem, all stem from the same frustration. Rockets, for all their power, are simply not a long-term solution. If humanity truly wants to leave Earth behind in a meaningful way, if it ever hopes to build something beyond just temporary outposts or research stations, then a new way of reaching orbit must be found. Whether it's an elevator stretching into the sky, a railgun firing payloads at impossible speeds, or some other method that is yet to be imagined, the reliance on massive, fuel-guzzling rockets is an obstacle that must eventually be overcome. The problem is not that people lack ideas. The problem is that space, for all its emptiness, remains stubbornly difficult to reach. But then again, so was flight once. So was crossing the ocean. So was everything, until it wasn't. 3. The Moon, our cosmic companion. Journey to the Moon. For most of human history, the Moon was nothing more than a distant light in the sky, a familiar but unreachable companion, always there but forever out of reach. It was the subject of myths, poems, and dreams, a place where gods and monsters were imagined to live, where lovers whispered under its glow, and where ancient astronomers mapped its shifting phases with careful precision. But then, in one small fraction of that history, everything changed. Rockets roared, metal touched lunar soil, and humans did something they had never done before. They left their world behind and set foot on another. The Apollo missions weren't just about proving that it could be done. They were a declaration, a statement that Earth was no longer the only place where humanity belonged. The journey to the Moon was, by any standard, a reckless, audacious gamble. The technology was rudimentary compared to what exists today. Computers with less processing power than a modern smartphone, rockets built with slide rules and human intuition, astronauts sitting atop controlled explosions, trusting that the numbers were correct. But somehow, through a mixture of genius, determination, and sheer human stubbornness, it worked. In 1969, when Neil Armstrong stepped onto the surface and left that first footprint, it wasn't just his own weight pressing into the dust. It was the weight of every person who had ever looked up at the night sky and wondered. The Apollo program continued for a few more years, each mission pushing a little further, staying a little longer, but eventually, the dream faded. Budgets were cut, political priorities shifted, and the Moon became, once again, a distant and unvisited neighbor. The last time a human stood on its surface was in 1972, and since then, it has remained untouched by human hands, a relic of a past ambition that seemed, for a time, abandoned. But now, after decades of absence, the Moon is calling again. The Artemis program is not just a return. It is an attempt to go further, to establish a lasting presence, to make the Moon something more than just a place humans visit for brief moments before leaving again. Unlike Apollo, which was about proving a point, Artemis is about laying a foundation, about setting up infrastructure that could one day lead to something bigger. A lunar base, a stepping stone to Mars, a testing ground for survival beyond Earth. It is not just about flags and footprints. It is about permanence. The plan is different this time. Robotic missions will scout ahead. Lunar orbiters will establish staging points. Astronauts will land in new regions, and technology will be built to sustain longer stays. There is even talk of extracting water ice from the Moon's poles, turning it into fuel, making the Moon not just a destination but a launch pad, a gateway to the rest of the solar system. What was once a place of myths and distant dreams is becoming something else entirely. The moon is no longer just a dead rock circling Earth. It is the first step towards something bigger, a test of whether humanity can truly exist beyond the place where it was born. It will not be easy. Space never is. But the fact that the effort is being made at all says something profound. After all these years, after all the setbacks, the hesitation, the delays, humans are finally looking up again, not just to admire, but to return. The moon's surface. The moon's surface is a place of silence, a world where nothing stirs, where the only movement comes from the occasional impact of a meteorite or the slow, imperceptible shifting of dust that has remained undisturbed for millions of years. It is a landscape frozen in time, marked by the scars of an ancient past, a surface that tells the story of a world without an atmosphere, without weather, without the soft erosion of wind or rain. Everything that has ever happened there is still written in its dust. Every impact, every disturbance, every footprint from the brief visits of astronauts still perfectly preserved, as if time itself forgot to move forward. Craters dominate nearly every part of the moon's surface, some small enough to be mistaken for mere indentations, others so massive that they stretch for hundreds of kilometers, their jagged rims casting long shadows under the harsh, unfiltered sunlight. The largest of them, the South Pole Aitken Basin, is an unimaginably vast wound in the lunar crust, over 2,500 kilometers across, the result of a collision so violent that it nearly cracked the moon to its core. These craters are not just scars. They are records of the violent history of the solar system, of a time when young planets and moons were battered by endless collisions, reshaped again and again by impacts that could have wiped out anything that tried to exist there. Unlike Earth, where erosion eventually smooths out the evidence of such violence, the moon has held on to its history, every crater a reminder of the chaos that once defined the early universe. But the moon is not just a land of destruction. Among the craters, there are great plains, vast, dark stretches known as the Maria, formed from ancient volcanic eruptions that flooded parts of the surface with molten rock, cooling into the smooth, dark expanses that now contrast so starkly with the surrounding highlands. These Maria, Latin four seas, were once mistaken for actual bodies of water by early astronomers, an illusion created by their dark, almost liquid appearance. In reality, they are the hardened remains of a time when the moon was still alive with volcanic activity, when lava still flowed beneath its surface, reshaping the landscape in ways that can still be seen today. There are mountains, too, towering ridges that rise dramatically from the lunar surface, relics of the same impacts that created the largest craters. Unlike the mountains of Earth, formed by the slow collision of tectonic plates, these were born in an instant, thrown up by unimaginably powerful forces, jagged and unweathered, their sharp peaks untouched by erosion. Among them is Mons Huygens, the tallest mountain on the moon, standing at over 5 kilometers high, its slopes bathed in an eternal stillness, its summit a place where no wind has ever blown, no water has ever carved the rock. And then, in the deepest shadows of craters near the moon's poles, there is something even more unexpected. Ice, locked away in places where sunlight never reaches, hidden in the coldest recesses of the surface. This ice has likely been there for billions of years, untouched, frozen in a world that should have no water at all. It is not just a curiosity. It is a resource, a potential key to future exploration, a source of water for astronauts, a possible means of producing fuel, an element that could make the moon more than just a destination. The presence of ice changes everything, turning the moon from a barren wasteland into something with potential, something that could support life, something that could be more than just a dead rock circling Earth. The surface of the moon is a contradiction. Lifeless, yet full of history, desolate, yet filled with possibilities. It is a place that has remained unchanged for billions of years, yet may soon become a stepping stone for the future of human exploration. Every crater, every mountain, every frozen shadow tells a story, not just of what the moon has been, but of what it could one day become. Lunar colonization. The idea of people living on the moon, building homes in a place where the sky is always black and the ground is covered in dust that hasn't been disturbed for billions of years, is something that once belonged purely to science fiction. But now, it's not just a fantasy. It's a plan, a real possibility that scientists and engineers are working to make happen. The moon, once thought of as a cold and lifeless rock, is slowly being seen as something more, a place where humans might one day build settlements, mine resources, and establish a foothold beyond Earth. The journey to making the moon livable, however, is not as simple as just landing and setting up a few structures. It's about figuring out how to survive in a place that was never meant for life, in an environment that offers nothing but rock, radiation, and silence. A lunar base would have to be more than just a shelter. It would have to be a self-sustaining home, a place where humans could live for months or even years without relying on constant shipments from Earth. Every detail, from where the base is located to how people will breathe, eat, and protect themselves from radiation, has to be carefully planned. Some of the most promising locations are near the moon's poles, where deep craters hide ice that has remained frozen for eons. That ice could be a lifeline, providing drinking water, oxygen for breathing, and hydrogen for rocket fuel, all of which would make long-term survival on the moon much more practical. But before anyone can start melting ice and filling oxygen tanks, there's the challenge of building the base itself. Unlike Earth, where construction is just a matter of assembling materials and following blueprints, building on the moon means dealing with an environment where even the smallest mistake could be deadly. Radiation is one of the biggest threats. With no atmosphere to block the sun's harsh rays and no magnetic field to shield against cosmic radiation, anyone living on the moon would be constantly exposed to levels of radiation that could cause serious health problems over time. One solution is to build underground, using the moon's own soil, regolith, to create thick protective walls. Some have even proposed setting up bases inside lava tubes, massive tunnels left behind by ancient volcanic activity that could provide natural shielding from radiation and meteorite impacts. Others suggest inflating habitats covered in layers of moon dust, using robotic 3D printers to construct protective shells before astronauts even arrive. No matter the method, the goal is the same: create a space where humans can live without constantly worrying about the environment trying to kill them. But survival isn't just about shelter. It's also about resources. The moon may look barren, but it holds valuable materials that could be the key to making lunar colonization possible. The surface is rich in metals like iron and titanium, which could be used to build structures and tools. There's also helium-3, a rare isotope that some believe could one day be used for fusion energy, offering a nearly limitless source of clean power. Mining these resources isn't as simple as sending bulldozers and dump trucks. It means designing machines that can operate in low gravity, withstand abrasive lunar dust, and function in extreme temperatures that swing from blistering heat to bone-chilling cold. If mining operations can be perfected, the moon could become more than just a home. It could become a supply station for deeper space exploration, a place where future missions refuel before heading to Mars and beyond. Yet, even with all the technical challenges, the biggest question remains: what would it actually be like to live there? Waking up every day to the sight of an unchanging, alien landscape, knowing that outside the walls of your base, there's nothing but vacuum and radiation. Eating food grown in artificial greenhouses, drinking recycled water, living in tight quarters with the same handful of people for months on end. It would be an existence unlike anything on Earth, demanding extreme discipline, adaptability, and a mindset capable of handling isolation on a level few have ever experienced. It wouldn't be easy, but it could be the first step towards something greater. The first time in human history that people live permanently on another world. The moon is harsh, but it's close enough to Earth that it's the perfect testing ground for humanity's next giant leap. If we can figure out how to survive there, how to use its resources, how to turn it into more than just a destination for short-term missions, then the dream of a truly spacefaring civilization becomes much more real. The first lunar settlers may not stay forever, but they will be the ones who prove that it can be done, that humans are not bound to Earth, that even the dead, airless surface of the moon can become a home. Theories on the moon's formation. There was a time when the moon didn't exist, when Earth spun alone in the vastness of space. unaccompanied by the pale companion that now dominates the night sky. Its presence feels so permanent, so essential to the way we perceive the world, that it's hard to imagine a time before it. And yet, the moon had to come from somewhere. It wasn't just placed in the sky, and it certainly didn't form the way Earth did. The question of where it came from has fascinated scientists for centuries, and while many theories have been proposed, one stands above the rest. The giant impact hypothesis, an idea that suggests the moon is the scar left behind by a cosmic catastrophe, a world born from destruction. The story begins over 4 billion years ago, in the violent, chaotic days of the early solar system, a time when space was a battlefield of forming planets, rogue asteroids, and uncountable collisions. Earth, still young, was a molten, unstable world, barely recognizable from what it is today. It was during this time, scientists believe, that a Mars-sized object, often called Theia, slammed into Earth with unimaginable force. The impact wasn't a simple crash. It was an event so violent that it briefly turned Earth into something unrecognizable. Theia didn't just bounce off or leave a crater. It merged, fusing with Earth in a hellish explosion that sent molten rock and debris flying into orbit. The sheer energy of the collision melted everything, vaporized massive portions of both Theia and Earth, and scattered their remains into space, creating a ring of molten material surrounding our broken world. This was the moment of the moon's birth, not as a solid body but as a chaotic disk of fire and stone, circling Earth in the aftermath of an event that should have been nothing but destruction. But physics has a way of finding order in chaos. Over time, that debris began to coalesce, tiny particles clumping together, drawn by gravity into larger and larger formations. Within thousands of years, an instant in cosmic time, what was once a cloud of shattered rock became a single body, cooling and solidifying into the moon as we know it. In its early days, it was much closer to Earth than it is now, looming larger in the sky, its surface still scarred by the molten remnants of its creation. The tidal forces between the two worlds were far stronger back then, shaping not just the moon's orbit but Earth's own rotation, slowly locking the moon into the synchronous orbit that keeps one face forever turned toward us. The evidence for this theory is written in the moon itself. Its composition is eerily similar to Earth's outer layers, as if it were carved from the same material, yet lacking the denser core elements that should be there if it had formed separately. The isotopic signatures in moon rocks, brought back by Apollo astronauts, match Earth's mantle, not some foreign celestial body. There are no massive deposits of volatile compounds on the moon, suggesting it was born from something that had been violently melted, not something that had cooled naturally over time. Every piece of data reinforces the idea that the moon is a part of Earth, a wound healed over billions of years into something that now feels like it was always meant to be there. And yet, despite the evidence, mysteries remain. Why was Theia the perfect size for this to happen? Did the moon form all at once? Or did it take multiple impacts to create what we see today? What happened to the remnants of Theia? Did they become part of Earth? Or are they still out there somewhere, silent and unrecognizable? There are also alternative theories, ones that suggest the moon was captured by Earth's gravity or that it formed alongside our planet from the same swirling disk of dust and gas. But none explain the evidence as well as the giant impact hypothesis. If this theory is true, then the moon is more than just Earth's companion. It is Earth itself, reshaped and reformed by the violence of the early solar system. It is a reminder that our planet's history is not one of gentle formation, but of chaos, collisions, and the relentless reshaping of worlds. The moon is a scar, but it is also a survivor, a permanent mark of the universe's indifference, and perhaps, in some strange way, proof that even destruction can lead to something beautiful. 4. The solar system's inner planets. Venus, the hellish planet. Venus is a world that defies expectation, a place that should have been Earth's twin but instead became a nightmare. It orbits the sun just a little closer than we do, its size and gravity eerily similar to our own, and in the distant past, it might have had oceans, rain, and a climate that could have supported life. But something went terribly wrong. Venus became a cautionary tale, a vision of what happens when a planet takes a different path, when the delicate balance of atmosphere and climate spirals out of control. It is a world where the sky is thick with poison, where the ground is hot enough to melt lead, and where any machine we send to explore is doomed to a rapid and brutal death. The atmosphere is the first thing that makes Venus an impossible place for life as we know it. It is a suffocating blanket of carbon dioxide so dense that standing on the surface would feel like being a kilometer beneath the ocean on Earth. The pressure is crushing, nearly 100 times what we experience at sea level, enough to squeeze and break most landers within minutes. But it isn't just the pressure that makes Venus hostile, it is the heat. The planet's thick clouds trap the sun's warmth in a runaway greenhouse effect, creating temperatures that soar beyond 450 degrees Celsius. It doesn't matter that Venus rotates so slowly that a day lasts longer than a year. There is no respite from the heat, no cool night to bring relief. The entire planet is an unbroken inferno, a place where even the hardest metals soften and lose their strength. The sky, instead of being a familiar blue, is a thick, choking yellow, filled with swirling clouds of sulfuric acid. The sun, if you could see it through the haze, would be a dim, angry glow, casting an eerie light over a landscape that looks more like something from a volcanic hellscape than a proper planet. The surface is cracked and dry, covered in vast plains of solidified lava, towering volcanoes, and deep fractures where the ground has split open from the heat. There are no rivers, no lakes, no signs of water in any form. Only a desolation that stretches in all directions, untouched by time except for the slow, relentless reshaping of the land by volcanic eruptions. Venus is a graveyard for spacecraft. The Soviet Union tried first, sending probe after probe, each one failing in increasingly dramatic ways. Some never made it to the surface, burning up or breaking apart in the thick atmosphere. Others managed to land, only to be crushed, melted, or silenced within minutes. Venera 7, the first to transmit data from the surface, lasted only 23 minutes before succumbing to the impossible conditions. Venera 13, one of the most successful, survived for about 2 hours before Venus did what Venus always does. It erased all evidence of foreign visitors. Even modern missions struggle with the idea of sending anything back. Unlike Mars, where rovers can explore for years, Venus gives us mere moments before swallowing whatever we send. But the most terrifying thing about Venus is what it tells us about Earth. The two planets started with similar conditions, and yet, for reasons we don't fully understand, Venus took a different path, one that led to a world completely inhospitable to life. It is a reminder that planets are not fixed, unchanging things. They evolve, sometimes in ways that make them unrecognizable, and sometimes in ways that turn them into places no living thing could ever survive. Scientists believe that billions of years ago, Venus may have had oceans, but as the sun grew hotter over time, the water evaporated, and with it, the planet's ability to regulate its climate. The carbon dioxide built up, the heat became unbearable, and Venus became the furnace it is today. It raises unsettling questions about our own future. Could Earth, given the right conditions, follow the same path? Could our own greenhouse gases, if left unchecked, create something similar? Venus is a worst-case scenario, an example of what happens when a planet loses control of its climate, a warning written in thick clouds and crushing heat. It is a place we may never walk on, never colonize, never truly conquer. And yet, it is one of the most important planets to study, not because it offers a future for humanity, but because it shows us a future we must avoid at all costs. Mercury, the scorched rock. Mercury is a planet of extremes, a place where the concept of day and night stretches beyond anything the human mind is used to. It is the closest planet to the Sun, a scorched and battered rock that has spent billions of years being cooked by unrelenting solar radiation. At first glance, it seems almost lifeless, an airless wasteland covered in craters, looking more like Earth's moon than a planet in its own right. But Mercury is not as simple as it appears. It is a world of violent contrasts, where the heat of the day can turn metal into liquid, yet just a few steps away in a permanently shadowed crater, water ice hides in the darkness, untouched for millions of years. The most brutal thing about Mercury is its temperature swings. It doesn't have an atmosphere to trap heat, so while the side facing the sun is blasted with temperatures soaring past 430 degrees Celsius, hot enough to melt lead, the night side plummets to an unimaginably frigid minus 180 degrees. This staggering difference is because Mercury rotates painfully slowly. A single day on Mercury, from sunrise to sunrise, lasts 176 Earth days. That means when the sun rises over the horizon, it takes weeks for it to move across the sky before finally setting again. During this time, the surface is baked relentlessly, absorbing the sun's energy without relief. Then, as the sun disappears, the heat bleeds away into space, leaving nothing but frozen rock behind. It's the kind of place where standing in one spot could incinerate you while just a short distance away, you could freeze solid in minutes. The landscape is a record of violence, a surface scarred by the impacts of countless asteroids and comets. Unlike Earth, where wind, rain, and plate tectonics constantly reshape the terrain, Mercury is a relic of the early solar system, a place that has barely changed for billions of years. Some of its craters are unimaginably vast, like the Caloris Basin, a giant impact scar over 1,500 kilometers across, created by an asteroid impact so powerful that it sent shockwaves rippling through the entire planet, creating strange, jumbled terrain on the opposite side. The surface is covered in a layer of fine, dusty regolith, crushed rock left behind by eons of collisions. There are cliffs, some stretching for hundreds of kilometers, that formed as Mercury's interior cooled and shrank, causing the crust to crack and fold over itself. The planet is still shrinking even now, a slow and unstoppable process that continues to shape its surface. But despite the heat and desolation, there is something strange about Mercury that defies expectations. Deep inside the craters near its poles, where sunlight never reaches, there is ice. Frozen water, locked away in eternal darkness, untouched by the sun's scorching rays. It seems impossible. How could a planet that spends half of its time being roasted by solar radiation hold onto ice? But these craters, deep enough and perfectly positioned, never see daylight, creating pockets of deep cold that have preserved ice for possibly millions or even billions of years. This discovery was one of the most surprising in recent planetary science, raising the possibility that comets and asteroids, which have bombarded Mercury for eons, left behind traces of water that managed to survive against all odds. Mercury is often overlooked because it lacks the atmosphere of Venus, the potential for life like Mars, or the moons of the outer planets that capture the imagination. It doesn't have rings, storms, or an active surface. It is simply a small, dense, and seemingly unremarkable rock hurtling around the sun at incredible speeds, orbiting faster than any other planet. But beneath its quiet, lifeless appearance, Mercury is a place that tells the story of the solar system's violent past, of collisions and chaos, of fire and ice, of a world that should have been erased by the sun, but instead continues to exist against all odds. It is a world that reminds us that even the most extreme places can hold unexpected secrets. Mars, humanity's next target. Mars has always had an undeniable hold on human imagination, a world that seems both impossibly alien and yet strangely familiar. It is cold, barren, and coated in rust-colored dust, a planet where the sky glows a faint, dusty pink, and towering volcanoes rise above desolate plains. It is a place where ancient riverbeds carve through the landscape, evidence of a time when water once flowed freely, when Mars might have been something entirely different. A planet with lakes, rivers, maybe even oceans. And yet today, it stands as a silent, frozen wasteland, a world that once had potential but lost it somewhere along the way. That simple fact is what makes it so enticing. It's not just another planet. It's a mystery, a possibility, a place where we see our own future and wonder. Could we live there? Could we bring it back to life? The evidence of water on Mars is one of the most compelling reasons we keep sending probes, landers, and rovers to its surface. The scars of ancient rivers and lakes are still there, visible even from orbit, as if the planet itself is frozen in time, holding on to the remnants of a past it can never reclaim. More than that, there are traces of water ice beneath the surface and at the polar caps, hidden reserves that could be the key to survival for any future explorers or settlers. Occasionally, dark streaks appear on slopes, thought to be seasonal briny water seeping through the soil before vanishing again. Water means potential, not just for life, but for sustaining human presence, for making Mars something more than a place to visit before turning back toward Earth. The missions that have touched down on its surface, Curiosity, Perseverance, Spirit, Opportunity, have been our eyes and hands on a planet we cannot yet reach ourselves. They have crawled across the dust, drilled into the rocks, and analyzed the atmosphere, sending back images that feel both thrilling and haunting. There are places on Mars where the terrain looks unsettlingly familiar, where it could almost be mistaken for a desert on Earth if not for the pale, eerie sky and the absence of anything living. These rovers have found organic molecules, methane spikes in the atmosphere, chemical clues that whisper of the possibility that Mars might not be as dead as it seems. Even if there is no life there now, maybe there was once. And if there was, then the question of why it vanished becomes one of the greatest puzzles we could ever solve. The idea of humans living on Mars, of transforming it into a second home, is both thrilling and daunting. It would take more than just sending astronauts and setting up a few habitats. Mars is a world that does not welcome life, a place where the thin atmosphere cannot protect against radiation, where dust storms can engulf the entire planet, where the cold is enough to freeze exposed flesh in seconds. Terraforming Mars, turning it into a place where humans could walk outside without a spacesuit, where plants could grow in open air, where rivers could once again flow, would be a task so monumental that it sounds almost like science fiction. Theoretically, we could thicken its atmosphere by releasing trapped CO2 from the polar ice caps, by building giant mirrors to reflect more sunlight, by setting off controlled explosions to warm the surface. But the reality is, even if we could do all of this, it would take centuries, possibly thousands of years. Yet, despite the impossibilities, despite the sheer scale of the challenge, the dream of Mars remains. Unlike other planets, it is within reach, a place that, with enough effort, could one day be made habitable, even if only in isolated domes at first. The first humans who set foot there will face a world where survival will be a constant battle, where every breath will have to be accounted for, where the landscape will be unforgiving. But they will also be pioneers in a way that no one has been before. Standing on the surface of another planet, looking up at a sky where Earth is nothing more than a bright, knowing that they are the beginning of something entirely new. It won't be easy, and it won't happen overnight, but Mars is waiting, silent and indifferent, yet full of possibilities. It is the closest thing we have to a blank slate, a chance to start over in a place that doesn't care whether we succeed or fail. The only question is whether we will take that step. 5. The Sun, the heart of our solar system. Solar flares and coronal mass ejections. How the Sun affects Earth. The Sun is not a calm, gentle ball of light that simply shines in the sky, warming the Earth and giving life to everything beneath it. It is a roiling, chaotic inferno of nuclear fusion, a place where gravity crushes hydrogen atoms together with such unimaginable force that they fuse into helium, unleashing energy that has sustained our planet for billions of years. But this constant, life-giving glow is deceptive because the Sun is not always peaceful. At times, it erupts with terrifying violence, sending vast explosions of plasma and radiation screaming into space. And when these outbursts are aimed at Earth, they remind us just how fragile our place in the cosmos really is. Solar flares and coronal mass ejections are among the most unpredictable and dangerous forces the Sun produces. A solar flare is a sudden burst of energy, an intense release of radiation that can travel at the speed of light, slamming into our atmosphere in mere minutes. These flares can disrupt radio communications, damage satellites, and expose astronauts to dangerous levels of radiation. But they are nothing compared to coronal mass ejections, enormous eruptions of solar plasma that hurl billions of tons of charged particles into space at staggering speeds. These waves of solar material don't just bathe the Earth in radiation. They carry with them the Sun's magnetic field, and when this collides with our own magnetic shield, the results can be spectacular or catastrophic, depending on the scale of the event. When a coronal mass ejection reaches Earth, its charged particles slam into our planet's magnetic field, distorting and twisting it in ways that can create dazzling auroras, lighting up the skies with ghostly ribbons of color. These displays, though breathtaking, are merely the side effect of something far more disruptive. When the sun unleashes a powerful enough storm, the currents it induces in the Earth's magnetosphere can surge through power grids, frying transformers, causing widespread blackouts, and knocking entire communication systems offline. The worst-case scenario would be something like the Carrington event of 1859, the most powerful geomagnetic storm ever recorded. Back then, telegraph lines sparked and caught fire, and the auroras were so bright that people reportedly read newspapers by their glow. If a storm of that magnitude hit today, it could cripple the internet, knock out satellites, disable GPS systems, and send modern civilization into a technological blackout that could take months or even years to fully recover from. We have satellites like the Solar and Heliospheric Observatory, SOHO, and the Parker Solar Probe keeping watch over the sun, scanning its activity for signs of brewing storms. But predicting solar weather is still an imperfect science. We know that the sun follows an 11-year cycle of increasing and decreasing activity, and that we are approaching a peak where solar storms will become more frequent and intense. But even with this knowledge, if a truly massive event were to be launched in our direction, there would be little we could do beyond shutting down vulnerable systems, hoping our power grids and satellites could endure the onslaught, and preparing for the fallout if they cannot. The sun has always been the source of life on Earth, but it is also a reminder that we exist at the mercy of forces far beyond our control. We build civilizations, we create technology, we push deeper into space, but all of it can be disrupted in an instant by a single temperamental outburst from the star at the center of our solar system. It is not something we can stop or prevent, only something we can try to understand and prepare for. And if the sun ever decides to unleash its full fury, we will be forced to confront the reality that for all our intelligence and progress, we are still just small, fragile beings living in the shadow of an ancient and unpredictable fire. The sun's energy. The sun is not just a ball of fire burning in the sky. It is a nuclear engine, an unfathomable inferno where atoms are crushed together under immense pressure, releasing energy that has sustained life on Earth for billions of years. Deep in its core, where temperatures soar to millions of degrees and pressures are so intense that matter behaves in ways that defy common sense, hydrogen atoms are forced together to form helium in a process known as nuclear fusion. Every second, the sun fuses hundreds of millions of tons of hydrogen, converting a fraction of that mass directly into energy, a relentless chain reaction that unleashes more power in a moment than humanity has ever produced in its entire history. This energy surges outward, battling against the sun's own gravity in a cosmic tug-of-war that has kept the star stable for eons. The light and heat from this process take an astonishing journey before reaching us. Photons, the fundamental particles of light, are born in the sun's core but do not travel freely. Instead, they are trapped in an endless maze of collisions, bouncing from atom to atom in a chaotic, random walk that can take thousands, even millions of years before they finally escape the sun's dense interior and make their way into space. Once free, however, they travel at the speed of light, crossing the 150 million kilometer distance to Earth in just over 8 minutes, a blink of an eye compared to the unimaginable time they spent trapped within the sun's depths. But the sun doesn't just bathe the Earth in light and warmth. It constantly sends out an invisible stream of charged particles known as the solar wind. This wind is born from the outermost layer of the sun's atmosphere, a superheated plasma so energetic that it escapes the sun's gravity entirely, rushing out into space in all directions. This relentless gale of solar material washes over the planets, stretching far beyond Pluto, sculpting the vast bubble of charged particles known as the heliosphere, the protective barrier that marks the true outer edge of our solar system. Earth's magnetic field acts as a shield against this wind, deflecting most of it harmlessly away. But at times, the sun's storms grow violent, and the solar wind intensifies into a raging tempest that can breach this shield, stirring up geomagnetic disturbances that disrupt power grids, scramble communications, and paint the skies with dazzling auroras. Beneath all of this, the sun's magnetic field is a restless, shifting force, twisting and tangling over time, creating vast loops of magnetic energy that erupt from its surface in the form of sunspots, flares, and coronal mass ejections. This magnetic chaos follows an 11-year cycle, flipping the sun's polarity like a vast cosmic reset button. As this cycle progresses, the sun grows more active, its surface peppered with dark, swirling sunspots, each one a region of intense magnetic turmoil, cooler than the surrounding surface but brimming with energy. Sometimes, these tangled magnetic lines snap and reconnect violently, releasing bursts of radiation and plasma that can tear through space, and, if Earth happens to be in their path, remind us just how much our modern world still depends on forces we barely understand. The sun is not a gentle, predictable entity. It is a churning, seething powerhouse, a cosmic engine that has been burning for over 4.5 billion years and will continue to do so for billions more. Yet, for all its raw, uncontainable power, it is also fragile in the grand scale of time. One day, when its hydrogen fuel is depleted, it will begin to change, expanding into a red giant, swallowing Mercury, Venus, and perhaps even Earth before eventually collapsing into a small, dense remnant of what it once was. But for now, it remains the heart of our solar system, a relentless source of energy and motion, the force that has shaped the planets, the weather, the tides, and every living thing that has ever existed on this small, fragile world. Future Dyson sphere and stellar megastructures. The idea of harnessing the full energy of a star is something that sounds like it belongs in the realm of distant science fiction, the kind of concept that only exists in the imaginations of writers and theorists who dare to dream about civilizations far beyond our own. But when you really think about it, it's a natural progression. As humanity continues to grow, as our technology expands and our hunger for energy becomes insatiable, the idea of building something truly massive, something that can tap into the raw, unfiltered power of a star, begins to feel less like fantasy and more like an inevitability. This is where the concept of a Dyson sphere comes in, a structure so vast, so ambitious, that it completely redefines what it means to manipulate the universe itself. A Dyson sphere, in its most extreme form, is an enormous shell or swarm of structures that fully encircle a star, capturing nearly all of its emitted energy. Right now, Earth only receives a tiny fraction of the sun's total output. Most of it is wasted, spilling out uselessly into space. A civilization that has reached the point where it needs more power than a single planet can provide would have no choice but to start looking outward. And the most efficient way to do that would be to build something that can tap into the very source of all energy in a solar system. This isn't some minor technological leap. It's the kind of thing that could only be attempted by a civilization vastly more advanced than ours, a Type 2 civilization on the Kardashev scale, one that has transcended planetary limitations and begun to manipulate entire star systems as if they were raw materials waiting to be shaped. But actually building something like this isn't as simple as imagining a giant sphere around the sun. The sheer amount of material needed to construct even a partial Dyson structure is beyond anything we currently have access to. A solid sphere, as some have proposed, would be impossible. It would collapse under its own gravity, and even if you could somehow stabilize it, the engineering challenges alone would be mind-boggling. A more realistic approach would be a Dyson swarm, a collection of millions or even billions of satellites orbiting the star in coordinated patterns, each one harvesting energy and transmitting it back to wherever it's needed. The construction of such a structure would require dismantling entire planets or asteroids, strip mining moons, and converting raw matter into vast networks of solar collectors, a process that would take centuries or even millennia. But in the grand scheme of a civilization's evolution, it might be a necessary step toward true sustainability. And if we go beyond just a Dyson swarm, there are even more extreme possibilities. Some have theorized structures like Dyson rings, where massive bands of energy-collecting stations orbit in stable formations, or even Dyson bubbles, where solar sails use the pressure of the star's radiation to hold their position, floating effortlessly in space while absorbing and redirecting energy. And then there's the ultimate possibility: star lifting, a process where a civilization doesn't just passively collect a star's energy, but actively controls it, manipulating its outer layers, extracting matter to be used as fuel or material, stretching the very fabric of the star's existence to suit its own needs. If that sounds unimaginable, consider the fact that if an advanced civilization were to ever reach this stage, they would barely resemble anything we currently understand as life. They wouldn't be struggling with the same problems we do, worrying about climate change or fossil fuels or energy shortages. They would have moved beyond those concerns entirely, operating on a scale so vast that even stars themselves become resources to be shaped and controlled. And yet, despite how alien that might seem, this could very well be the future. Maybe not for us, maybe not for thousands of years, but somewhere out there in the universe, if life is common and civilizations endure, it seems almost inevitable that some form of stellar megastructure will one day be built. And if we ever detect one, if we ever look into the sky and see an inexplicable dimming of a distant star, one that flickers in a way that suggests something unnatural, something vast and constructed rather than chaotic and random, then we will know, without a doubt, that we are not alone. Not only that, but we will know that somewhere, out there in the vastness of space, someone has already walked the path we have yet to tread. Someone has already reached beyond their homeworld and reshaped the heavens in ways we can only dream of. 6. The asteroid belt and dwarf planets. Asteroids. Potential for mining or threats to Earth. Asteroids are the leftovers, the remnants of a chaotic past, pieces of a world that never was. The asteroid belt itself, that vast collection of rocky bodies orbiting between Mars and Jupiter, is often imagined as a dense field of tumbling debris, an almost impassable gauntlet of colliding stones. But in reality, it's nothing like that. The space between these asteroids is enormous, and if you were drifting through, chances are you wouldn't even see another one nearby. And yet, despite their quiet existence, asteroids hold both promise and danger in equal measure. On one hand, they could be the key to humanity's future in space. They're rich with materials: iron, nickel, platinum, even water ice. All the essential resources we would need to expand beyond Earth without having to haul everything from the surface of our planet. Some of these asteroids contain more metal than has ever been mined in human history, and if we ever get serious about deep space industry, mining them will be inevitable. Imagine spacecraft designed to latch onto these wandering rocks, breaking them apart, extracting valuable metals, and sending refined materials back to wherever they're needed. Colonies could be built in orbiting factories, entire industries could flourish in the void, and a single, well-placed asteroid mining operation could produce wealth beyond anything seen on Earth. But like anything that involves space, the biggest challenge isn't just getting there. It's making it practical, affordable, and safe. Mining an asteroid is easy to dream about, but how do you transport the material? How do you refine it in zero gravity? How do you stop the asteroid itself from shifting in unpredictable ways? These aren't just small problems. They're massive engineering puzzles that need solving before we can even consider large-scale asteroid mining as a real industry. And then there's the other side of the equation, the part that isn't about progress or wealth, but about survival. Because every so often, an asteroid reminds us that it's more than just a rock floating harmlessly in space. It's a potential bullet aimed at Earth, a reminder that our planet has been hit before and will be hit again. We see the evidence all around us, from the massive craters carved into the surface of our world to the extinction-level event that wiped out the dinosaurs. The question has never been if an asteroid will hit us again. It's when. Some near-Earth objects pass uncomfortably close, slipping by at distances that, on a cosmic scale, might as well be a near miss. Astronomers track thousands of them, mapping their orbits, calculating probabilities, trying to predict whether one of them might eventually come a little too close. And if one does, if the calculations ever show an impact is inevitable, then humanity will have a decision to make: do nothing and hope for the best, or attempt something we've never done before. actively prevent a planetary disaster. We've already taken the first steps. NASA's DART mission successfully changed the trajectory of an asteroid, proving that with enough force, we can nudge these space rocks off their paths. But that was a small-scale test, a controlled experiment. A real threat, a world-ending asteroid, would be another challenge entirely. Do we try to deflect it with more kinetic impactors? Do we use nuclear explosions to alter its course? Do we try something even more ambitious, like attaching a massive thruster to push it away? The answer isn't clear, and we can only hope we never have to find out the hard way. Asteroids are both our greatest untapped resource and a lurking danger that could erase everything we've built. They are time capsules of the solar system's birth, frozen pieces of a violent past that could shape our future in ways we're only beginning to understand. Whether they become our stepping stones into a new era of space exploration or the cause of the next great extinction depends entirely on what we do next. Ceres and Vesta. Ceres and Vesta are the kind of places that make you question what a planet really is. Neither of them quite fits the mold. Both are relics of a time when the solar system was still finding its shape, and yet they couldn't be more different. If you stood on Vesta, you'd be on a world that never finished forming, a battered rock with a history of violent impacts, where the ground beneath your feet would be nothing but shattered pieces of ancient crust. If you stood on Ceres, you'd be on something far stranger. A world that hides water beneath its surface. A place that almost feels like it should have been something more, like it was caught between being an asteroid and a planet and never quite managed to become either. Vesta is the survivor of something brutal. It's one of the largest objects in the asteroid belt, and yet, it feels like a world that has already lived through its apocalypse. Its surface is scarred by impacts so large they reshaped the entire structure of the asteroid itself, exposing layers that should have stayed buried deep underground. One of its biggest craters, Rhea Silvia, is so massive that it's almost ridiculous. Over 500 kilometers across, nearly as wide as Vesta itself. If Earth were hit by something that size, there would be nothing left to write about. But Vesta held on, and what's left is a world of jagged cliffs, fractured terrain, and signs that, once upon a time, it might have had a molten core, a hint that for a brief moment, it could have been on the path to becoming something greater. Meteorites from Vesta have even made their way to Earth, meaning that we've held pieces of it in our hands long before we ever sent a spacecraft to see it up close. Ceres is something entirely different. It's the only dwarf planet in the asteroid belt, a place where ice and rock coexist in a way that shouldn't make sense, a world where water seems to hide just beneath the surface. Unlike Vesta, which is all solid rock and battered crust, Ceres is coated in a layer of material that suggests a far more complicated history. When NASA's Dawn spacecraft got close enough to see it in detail, one of the first things that stood out was a series of bright spots. Highly reflective patches inside craters that turned out to be salt deposits left behind by water that had once seeped up from below. That alone was enough to make Ceres more interesting than anyone had expected, because where there's water, there's always the possibility of something even more fascinating. It doesn't mean life ever existed there, but it does mean that Ceres has the right conditions for something to have happened in the past. The idea that there's liquid water beneath its surface is something scientists are still trying to prove, but there's evidence that, at some point, Ceres had enough internal heat to keep some of that water from freezing completely. Maybe there's still a slushy, briny ocean trapped below, slowly pushing up through cracks in the surface. Maybe there were even cryovolcanoes. Volcanoes that don't erupt with molten rock, but with water and ammonia, freezing instantly in the vacuum of space. The more we look at Ceres, the more it starts to feel less like a large asteroid and more like a lost moon, the kind of world that wouldn't be out of place orbiting Jupiter or Saturn instead of drifting alone in the asteroid belt. Both of these worlds tell a different story about what could have been. Vesta is what happens when a planet's foundation is shattered before it ever gets the chance to grow, a glimpse at what the early solar system must have been like, chaotic and brutal. Ceres, on the other hand, is a world of quiet possibilities, a place where something as simple as buried ice could change everything we know about the history of water in our solar system. Neither of them will ever be home to life as we know it, but they hold secrets about the past, about the way planets form, and about what might still be waiting in the cold, dark spaces between the stars. Pluto and Kuiper Belt. Pluto was never just a tiny dot on the edge of the solar system, no matter how it was labeled. It was always something more, something that didn't quite fit the categories we made. And when the New Horizons spacecraft finally got close enough to show us what it really was, everything changed. This wasn't some frozen, lifeless rock drifting in the dark. It was a world with an atmosphere, glaciers of nitrogen, mountains made of water ice, and a surface so young in places that something had to be reshaping it. It was dynamic, unpredictable, and far more alive than anyone had expected from a place so distant and cold. And the more we learn about Pluto, the more it feels like it was never alone out there, because beyond it lies the Kuiper Belt, a vast and mostly unexplored region filled with other worlds that might be just as strange, waiting for their moment to be discovered. Pluto's atmosphere is one of its most bizarre features because it shouldn't even be there. The sunlight that reaches Pluto is weak, just a faint glow compared to what we get on Earth. And yet that tiny amount of warmth is enough to vaporize nitrogen and methane on Pluto's surface, creating a delicate atmosphere that clings to the dwarf planet. Unlike Earth's thick, breathable air, Pluto's atmosphere is so thin that standing there, if you could survive the cold, would feel like standing in a vacuum. But the interesting part is that it isn't static. As Pluto moves through its long, elliptical orbit, getting closer to and farther from the Sun, its atmosphere expands and contracts, sometimes freezing and falling back onto the surface like a slow, quiet snowfall of nitrogen ice. When New Horizons passed by in 2015, it caught an incredible sight: Pluto's sky glowing blue, not because it has an atmosphere like Earth's, but because tiny particles scatter the light in a way that makes it look eerily familiar. But Pluto is only one piece of the puzzle. It's not the only dwarf planet out there, not even close. The Kuiper Belt is filled with objects that defy expectations, places like Eris, which is even smaller but so dense and reflective that for a while, it was thought to be the real ninth planet. Make, which has an icy surface that reflects sunlight like fresh snow, and Haumea, an elongated, rapidly spinning world that stretches the very definition of what a planet should look like. These are the ghosts of a solar system that could have been, small planets that never made it past the chaotic early years, stuck in the frozen outskirts while the inner planets grew into the worlds we know today. The Kuiper Belt itself is like the asteroid belt, but colder, farther, and much more mysterious. It's a region of icy remnants from the solar system's formation, a place where everything moves in slow motion under the weak pull of the sun's gravity. Most of these objects are still unknown, their surfaces untouched, their compositions a mystery. And yet, they might hold some of the oldest, most pristine material left from the birth of the solar system, frozen in time, waiting for us to reach them. Pluto's demotion from planethood was never about what it was, only about where we decided to draw the lines. But standing on its surface, looking up at its hazy blue sky, knowing that it has mountains, valleys, glaciers, and a strange, beating geological heart, it's hard to call it anything other than a world. And if Pluto is that fascinating, then what else is waiting for us in the distant reaches of the Kuiper Belt? Maybe it's time to stop thinking about planets as the only things worth exploring and start wondering what secrets are hiding in the frozen corners of the solar system, where the sun is just another distant star in the sky. 7. The gas giants and their moons. Jupiter, king of planets. Jupiter isn't just a planet. It's a force of nature, a world so massive that if it were just a little bigger, it might have ignited into a second sun. Everything about it is extreme, from its crushing gravity to its ever-churning atmosphere, a swirling chaos of storms and winds that never stop. The most famous of them, the Great Red Spot, has been raging for at least 400 years, a hurricane so enormous that it could swallow Earth whole. It's not just a storm, it's a statement, a reminder that Jupiter operates on a scale that makes human concerns feel small. But what's even stranger is that we don't actually know why it's red. Scientists have theories. Maybe it's the way sunlight interacts with chemicals in its upper atmosphere. Or maybe it's something deeper, something hidden beneath layers of gas and pressure so intense that they turn hydrogen into a metallic liquid. Either way, Jupiter doesn't give up its secrets easily. The planet's radiation is another thing that makes it completely unwelcoming to anything resembling life as we know it. Jupiter's magnetic field is the strongest of any planet in the solar system, a vast and invisible structure that traps particles and turns its surroundings into a radiation hellscape. Any spacecraft that lingers too long in its vicinity risks being fried by this relentless bombardment, and even Jupiter's own moons aren't safe. Io, the most volcanic body in the solar system, is constantly being tormented by Jupiter's gravity and radiation, its surface a tortured landscape of erupting lava and sulfur snow. But Jupiter isn't just a destroyer, it's also a protector. Its immense gravity acts like a cosmic shield, pulling in comets and asteroids that might otherwise threaten Earth. In 1994, the world watched as the Shoemaker-Levy 9 comet was torn apart and consumed by Jupiter's atmosphere, each impact leaving scars the size of entire continents. If Jupiter weren't there, taking these hits for us, Earth might have faced far more catastrophic impacts throughout its history. And yet, for all its violence, Jupiter is also a world of mysteries. Deep beneath its cloud tops, we don't know if there's a solid core or if the pressure just keeps increasing until atoms themselves are crushed into something unrecognizable. Its atmosphere is made mostly of hydrogen and helium, but there are hints of water, ammonia, and other complex molecules swirling in the depths. Some scientists even speculate that, far below the crushing weight of its clouds, there might be strange, alien forms of weather. Perhaps metallic rain or storms unlike anything seen on Earth. Jupiter isn't just the biggest planet in the solar system. It's a reminder of how wild and unpredictable the universe can be. It's a world where storms never die, where gravity bends reality, and where the rules that apply to Earth start to break down. Every time we send a probe past it, we learn something new, and yet it always leaves us with more questions than answers. Jupiter is a giant, a guardian, a mystery wrapped in storms, and no matter how much we study it, it always finds a way to surprise us. Europa, subsurface ocean and possibility of alien life. Europa is the kind of place that makes you question everything you thought you knew about life in the universe. At first glance, it's just another frozen moon orbiting a gas giant, a ball of ice locked in the endless gravitational grip of Jupiter. But beneath that icy shell, there's something incredible. A vast, hidden ocean, kept liquid by the relentless push and pull of Jupiter's gravity. It's not just a small underground lake or some scattered pockets of water trapped in ice. It's an entire world of liquid stretching beneath the entire surface, containing more water than all of Earth's oceans combined. And where there's water, there's a chance for life. The surface itself is a chaotic landscape, crisscrossed with deep cracks and ridges where the ice shifts and breaks apart, revealing fresh, younger ice underneath. Occasionally, massive plumes of water erupt into space, spraying material from deep within Europa's ocean. These geysers are like cosmic breadcrumbs, hinting at what lies beneath without the need to drill through miles of ice. They tell us that something is moving down there, something powerful enough to force water up into the vacuum of space. Scientists have already found traces of salts and organic molecules in these plumes, tantalizing signs that the ocean isn't just water, but a chemically rich environment that might support life. The question isn't just whether there's life on Europa, but what kind of life it could be. If anything does exist down there, it wouldn't be sun-loving, photosynthesis-driven creatures like we have on Earth. Instead, it would be something more like the strange ecosystems we've found in Earth's deep oceans, where life survives in the crushing dark, feeding off heat and minerals from hydrothermal vents. If Europa has vents like that at the bottom of its ocean, they could be creating the perfect conditions for alien microbes, or even something more complex. Imagine entire networks of bizarre, alien organisms living in a world cut off from sunlight, evolving in ways we can only guess at. But Europa isn't exactly inviting. That ice shell, while cracked and constantly shifting, is still miles thick, and Jupiter's brutal radiation bombards the surface constantly, making it one of the most hostile places in the solar system. Any future mission that wants to search for life there will have to find a way to get past the ice, either by drilling through it or sending a probe to dive into the plumes and analyze the water directly. NASA's upcoming Europa Clipper mission is the first real step toward answering these questions, designed to fly past the moon dozens of times and scan it in ways we've never been able to before. If the mission finds strong evidence of organic molecules, energy sources, or even chemical imbalances that hint at biological activity, it could be the closest thing we've ever had to proof that we're not alone. Europa has always been one of the most promising places to search for extraterrestrial life, not because it's anything like Earth, but because it isn't. It's a reminder that life, if it exists beyond our planet, doesn't have to follow Earth's rules. It could be thriving in places we'd never expect, hidden beneath ice, waiting for us to finally look in the right place. And if we ever do find something swimming in those dark alien waters, it won't just change how we see Europa. It'll change everything. Ganymede, largest moon and own magnetic field. Ganymede doesn't just settle for being the largest moon in the solar system. It goes further, doing things no other moon dares to do. It has its own magnetic field, something no other moon possesses, which means that in the grand chaos of Jupiter's radiation-blasted neighborhood, Ganymede has carved out a space where things work a little differently. A magnetic field is normally something you associate with planets, not moons, but here it is, shielding parts of Ganymede from Jupiter's relentless storms of charged particles. It even has auroras, ghostly ribbons of light shimmering in its thin atmosphere, flickering as Jupiter's massive magnetosphere tugs at them. This moon, orbiting the king of planets, behaves more like a planet itself, and that alone makes it stand out in a way that's impossible to ignore. Its surface is a mosaic of contradictions. Vast swathes of ancient, cratered terrain sit beside regions that are smoother and younger, as if Ganymede tried to renew itself over time but never quite finished the job. There are enormous grooves and ridges stretching for thousands of miles, the scars of past tectonic forces that reshaped its landscape. Unlike Europa's constantly shifting ice shell or Io's volcanic chaos, Ganymede seems to exist in a state of frozen change, a world that moved and reshaped itself in the distant past, but has since slowed down, as if it's waiting for something to wake it up again. And then there's the real mystery lying beneath its surface. Like Europa, Ganymede is believed to have a hidden ocean, locked under miles of ice, possibly containing more water than all of Earth's oceans combined. But Ganymede is bigger, colder, and more complex, and its ocean might be buried so deep that it exists as layer upon layer of different phases of ice and liquid, stacked in a way that makes it even harder to reach than Europa's relatively accessible subsurface sea. If there is life in Ganymede's waters, it would have to endure extreme pressures and possibly rely on some deep, hidden energy source, far beyond anything Earth's life forms have ever had to deal with. Despite its size and its magnetic oddities, Ganymede has remained strangely in the background compared to its more famous siblings like Europa and Io. But that's starting to change. Missions like NASA's Europa Clipper and the European Space Agency's JUICE, Jupiter Icy Moons Explorer, are finally turning their attention toward this behemoth, aiming to map its surface, analyze its ocean, and try to understand what's really happening beneath that thick crust of ice. If there's one thing the solar system has taught us, it's that places we once overlooked often turn out to be the most interesting. Ganymede might not have the drama of Io's eruptions or Europa's tantalizing plumes, but it holds secrets of its own. Secrets that, when uncovered, could completely reshape our understanding of what a moon can be. Saturn, the jewel of the solar system. Saturn doesn't need to try too hard to impress. While Jupiter looms as the solar system's undisputed heavyweight, Saturn is the one that gets all the admiration. Its rings alone make it a spectacle, an impossibly delicate system of ice and rock stretching out like a cosmic masterpiece. Up close, those rings aren't the smooth, solid halos they appear to be from a distance. They're chaotic, constantly shifting, with countless particles ranging from dust grains to boulder-sized chunks, all caught in a delicate gravitational dance. Some parts of the rings are young, possibly formed from shattered moons, while others may be ancient, remnants of the solar system's earliest days. The entire system is in flux, a grand but temporary feature that might not last forever. Saturn's rings could fade over millions of years, either dispersing into space or raining down onto the planet itself, erasing one of the most iconic sights in the solar system. But Saturn isn't just about appearances. Its atmosphere is a stormy, turbulent place, swirling with bands of cloud layers that form strange hexagonal wind patterns at its poles, an anomaly that still puzzles scientists. Beneath that thick atmosphere lies a core of unknown composition, a deep mystery hidden beneath crushing pressures and unrelenting gravity. Unlike Jupiter, whose storms are violent and colorful, Saturn seems subdued in comparison, but the sheer scale of its systems, its winds, and its storms remind us that there's nothing truly calm about a gas giant. And then there's Titan, Saturn's largest moon, a world so bizarre it could pass as an alien planet in its own right. It has an atmosphere thicker than Earth's, a hazy golden shroud of nitrogen and methane that obscures the surface. But the real wonder lies below that thick smog. Titan is the only place beyond Earth known to have liquid lakes and rivers. Except here, it's not water carving out the landscape, but liquid methane and ethane, flowing like rivers, pooling into lakes, evaporating into clouds, and falling as rain in a bizarre, frigid version of the water cycle we know on Earth. The surface itself is sculpted by dunes of frozen hydrocarbons and icy bedrock, an environment so extreme that water, if present, would be as solid as rock. Titan is a world that defies expectations. It has weather, seasons, a thick atmosphere that could support wind-driven waves on its methane lakes, and possibly even conditions that could support exotic forms of life. While life as we know it needs water, there's speculation that Titan could harbor completely alien chemistry, where liquid hydrocarbons serve as the medium for life to evolve in a way we've never seen before. And beneath all of this, deep under the icy crust, there may be a hidden ocean of liquid water, adding yet another layer of possibility to this enigmatic world. Saturn may be the jewel of the solar system, but its moons, especially Titan, are what give it depth, mystery, and potential for discovery. With future missions planned, including NASA's Dragonfly drone, which will fly across Titan's surface exploring its lakes and dunes, we are only beginning to scratch the surface of what this gas giant and its strange, fascinating moons have to offer. Titan, thick atmosphere and rivers of liquid methane. Titan feels like the kind of place that shouldn't exist, at least not in the form that it does. It's Saturn's largest moon, but calling it just a moon doesn't quite capture what makes it so strange. If you dropped it somewhere in the solar system without context, it might even pass for a planet. It has a thick atmosphere, the only moon in the entire solar system that can make that claim, and that alone makes it feel more like a world than just a satellite orbiting a gas giant. The air there is mostly nitrogen, like Earth's, but laced with methane, giving it a permanent haze that cloaks the surface in an orange glow. It's thick enough that if you were standing there, you wouldn't need a pressure suit. Just an oxygen mask and protection from the cold. And cold doesn't even begin to describe it. At nearly minus 290 degrees Fahrenheit, minus 179 degrees Celsius, Titan is a world where water is as solid as rock, but methane, a gas on Earth, flows like water. The surface, if you could see through the dense, golden atmosphere, is a place of contrasts. Dry dunes stretch across vast plains, shaped by winds just like on Earth, except these dunes aren't made of sand, but tiny grains of frozen hydrocarbons. Then there are the lakes, dark, liquid pools of methane and ethane, some of them as large as seas. It's the only other place we know of where liquid stands on the surface in stable bodies, eroding the landscape, carving out channels, creating river deltas, and even producing rainfall in an alien version of the water cycle. When it rains, it's not water but methane, falling from hydrocarbon clouds, hitting the ground in slow, heavy droplets, forming puddles that feed back into the lakes in a cycle eerily similar to Earth's. Except here, everything is different, adapted to a chemistry so unfamiliar it feels like a science fiction writer's dream. Beneath the frozen surface, Titan hides another secret. An ocean, deep under miles of ice, made of liquid water. It's trapped beneath the thick crust, possibly warmed by tidal forces from Saturn's gravity. This means Titan isn't just a world of exotic methane lakes. It could also have a buried, hidden ocean like Europa or Enceladus, one that might hold the potential for life. The surface itself may be too harsh and too alien for Earth-like biology, but that underground ocean, sealed away from the brutal cold, is another story entirely. If there's life anywhere in the solar system beyond Earth, Titan might just be one of the best places to look, even if the kind of life it could support might not be anything like what we expect. NASA's Dragonfly mission, set to launch later this decade, will finally give us a chance to explore Titan up close in a way never done before. Instead of just another lander, it will be a flying drone capable of moving across the landscape, hopping between different locations, and giving us a real look at this eerie, frozen world. It's the kind of place that keeps reminding us how little we really know about the possibilities of other planets, moons, and environments so different from our own. Titan, with its methane lakes and thick, unbreathable air, seems inhospitable at first glance. But it's alive in its own way. Weather, rivers, erosion, rain, and an entire system of chemistry playing out on a frozen stage, waiting for us to finally understand it. Enceladus, water plumes, and potential for life. Enceladus shouldn't be as interesting as it is. At first glance, it's just another icy moon orbiting Saturn, a frozen world barely 500 kilometers across, seemingly locked in an existence of quiet desolation. But the more we looked, the stranger it became. The Cassini spacecraft, which spent over a decade studying Saturn and its moons, discovered something unexpected. Plumes of water vapor spraying into space from Enceladus's south pole. These weren't just small wisps of mist. They were massive geysers stretching hundreds of kilometers into space, composed of water, organic molecules, salts, and even hints of hydrogen gas. Something beneath the surface wasn't just frozen and dead. It was active, alive in a geological sense, churning and interacting in ways that no one had expected. That was the first clue that Enceladus had an ocean, not just any ocean, but a deep, subsurface sea hidden beneath its icy crust. The plumes weren't just some random phenomenon. They were the result of water being forced up through cracks in the ice, likely caused by the immense gravitational pull of Saturn. Tidal forces constantly flex and bend the moon's interior, generating enough heat to keep a massive underground ocean in a liquid state despite the frigid temperatures on the surface. And wherever there's liquid water, the natural question follows. Could there be life? This isn't just speculation for the sake of excitement. The water plumes that Cassini flew through contained organic compounds, carbon-based molecules that are some of the fundamental building blocks of life as we know it. More than that, the detection of molecular hydrogen suggested something even more tantalizing: hydrothermal vents at the bottom of Enceladus's ocean. On Earth, these vents exist deep in the abyssal depths of our own oceans, where scalding water, rich in minerals, seeps from the seafloor. Despite the total absence of sunlight, life flourishes around them, feeding off the chemical energy rather than photosynthesis. If similar vents exist on Enceladus, then there's a real possibility that something, microbes, bacteria, or even entirely unknown forms of life, could be thriving in the dark, salty depths of this hidden ocean. The idea of an entire alien ecosystem buried beneath kilometers of ice, surviving in ways that mirror life on Earth's seafloor, is one of the most intriguing possibilities in astrobiology. Unlike Mars, where past life is more of a guesswork endeavor, Enceladus offers something entirely different. A world where liquid water is actively interacting with rock, where chemistry is happening right now, where the ingredients for life aren't just theoretical but confirmed. The only question left is whether or not something has actually taken that next step and become alive. Future missions to Enceladus aren't just a matter of curiosity. They could be one of the best chances humanity has at finally answering the age-old question of whether life exists elsewhere. Unlike Mars, where we have to dig through rock and analyze soil samples, Enceladus is doing the hard work for us. It's actively spraying its ocean into space, offering a direct sample of what lies beneath without needing to drill or land. If there's something there, microbes, chemical signatures, or even something completely unexpected, it might be drifting in those plumes, waiting for us to finally take a closer look. Enceladus is more than just an icy moon. It's a doorway to the possibility that life isn't unique to Earth, that beneath the frozen surface of a tiny Saturnian moon, something else might be out there, surviving, evolving, and existing entirely independent of our planet. Uranus and Neptune, the ice giants. Uranus and Neptune don't get the same level of attention as Jupiter and Saturn, and maybe that's because they sit so far out in the solar system, distant and quiet, seemingly unchanging. But they are anything but boring. These two ice giants, wrapped in thick atmospheres of hydrogen, helium, and methane, are some of the strangest and most unexplored worlds we know of. Unlike the gas giants, which are dominated by swirling clouds and enormous storms, Uranus and Neptune have atmospheres filled with ices, water, ammonia, and methane frozen into their thick, slushy interiors. Methane, in particular, is what gives them their distinct blue color, absorbing red light and scattering the cool, deep blues that make them look like frozen, distant ghosts of the solar system. Uranus, in particular, is just bizarre. It doesn't spin the way the rest of the planets do. While most planets rotate with their poles more or less upright relative to their orbits, Uranus is completely sideways, tilted over by 98 degrees. It essentially rolls around the sun like a knocked-over marble, its poles taking turns facing the sun directly for decades at a time. This kind of extreme tilt isn't something that just happens on its own. It suggests a catastrophic event in the past, likely a massive collision with a planet-sized object that completely upended its rotation. This means that Uranus experiences some of the strangest seasons in the solar system, with one hemisphere plunged into total darkness for over 40 years before the cycle flips and the other side gets its turn. The effect this has on its weather is still something of a mystery. Its pale blue clouds seem almost eerily calm compared to the violent storms of Jupiter or the deep, churning bands of Saturn. But beneath that quiet surface, it's likely that strong winds and atmospheric currents are still shaping the planet in ways we don't yet understand. Neptune, on the other hand, is anything but quiet. It might sit at the edge of the solar system, cold and distant, but it has some of the most extreme weather known. Winds on Neptune scream across the planet at speeds reaching over 2,000 kilometers per hour, faster than the speed of sound. This makes them the strongest winds in the entire solar system, moving with a force that would tear apart anything that dared to exist in them. Despite being over 4 billion kilometers from the sun, Neptune somehow generates enough energy to power these ferocious storms, including massive dark spots, Earth-sized tempests that appear and disappear with little warning. These storms are similar to Jupiter's Great Red Spot, but are far more transient, coming and going over the course of a few years rather than persisting for centuries. Beneath their atmospheres, both Uranus and Neptune likely don't have solid surfaces in the way we think of terrestrial planets. Instead, they have deep layers of slushy, superheated water and ammonia surrounding dense, rocky cores. But what's even stranger is what might be happening inside those layers. Scientists believe that the extreme pressures within these planets may actually turn carbon into diamonds, creating literal diamond rain that falls through the thick, ice-rich atmospheres. If this is true, then Neptune and Uranus could be home to entire layers of liquid diamond, sinking toward the core in a way that sounds more like science fiction than reality. Despite all of this strangeness, we've barely studied these two planets. The only spacecraft to have visited them was Voyager 2, which flew by Uranus in 1986 and Neptune in 1989, capturing stunning images but leaving far more questions than answers. Since then, they've been left in the dark, distant, and unexplored, waiting for another mission to finally take a closer look. Given how much we still don't know about their atmospheres, their moons, and their mysterious, deep interiors, sending another probe to these forgotten ice giants is long overdue. In a solar system filled with gas giants, rocky worlds, and icy moons, Uranus and Neptune remain outliers, strange and unexplored, holding secrets about planetary formation, extreme weather, and the nature of ice-rich worlds that might be common across the galaxy. Triton, Neptune's captured moon and ice volcanoes. For all the strange and violent things happening on Neptune itself, its largest moon, Triton, might be even more unusual. Unlike any other major moon in the solar system, Triton orbits Neptune backward. completely against the planet's rotation, something that immediately suggests it wasn't born there. It's a stolen world, a wanderer that Neptune captured long ago, probably a former Kuiper Belt object like Pluto that got too close and was trapped by Neptune's gravity. This backward orbit is a death sentence in the long run because tidal interactions are slowly dragging Triton inward, meaning that one day, millions or billions of years from now, it will spiral too close and be ripped apart, forming a spectacular ring system before eventually disappearing entirely. But for now, Triton remains, defying expectations at every turn. Its surface looks like something straight out of science fiction, a frozen wasteland covered in nitrogen ice, sculpted by forces that we're still trying to fully understand. Voyager 2, the only spacecraft to ever visit Triton, revealed a landscape that looked bizarrely smooth in some places, as if parts of the moon had been recently resurfaced. That's not something you'd expect from a cold, distant world that should be geologically dead. But Triton isn't dead. It's very much alive, reshaping itself with forces that seem impossible for a moon so far from the sun. The biggest clue to this came from Voyager 2's images, which showed something incredible. Black streaks stretching across the moon's surface, evidence of geysers erupting from below. But these weren't ordinary geysers spewing water like on Enceladus or Europa. These were cryovolcanoes, shooting nitrogen gas into the thin, wispy atmosphere, like Earth's geysers, but frozen to an extreme. The idea of volcanoes on a frozen world is already strange, but what makes Triton's ice volcanoes even more interesting is how they work. They aren't driven by the same kind of internal heat that powers volcanic activity on Earth or Io. Instead, they rely on something much more subtle: the weak warmth from the sun, which is barely strong enough to reach Neptune, but somehow still manages to penetrate Triton's surface, heating up pockets of nitrogen ice just enough to make them burst like a shaken soda can. The eruptions send gas and dust high into the sky, creating dark streaks that slowly settle back down. And since this process constantly renews parts of the surface, it explains why Triton looks so much smoother than expected, as if it's constantly refreshing itself, while other frozen moons remain scarred and cratered from impacts. If that wasn't enough, Triton's thin atmosphere, mostly nitrogen with traces of methane, behaves in a way that's eerily familiar. It's so cold that it collapses onto the surface during the long Neptunian winter, essentially freezing out of existence, only to return as a gas when the seasons shift and temperatures rise again. This means Triton's atmosphere isn't static. It changes over time, cycling between gas and ice in a way that has never been seen on any other large moon. It's almost like a distant, frozen echo of what happens on Earth, just on an alien scale. Beyond its atmosphere and volcanic activity, there's the even bigger question: what's happening beneath Triton's surface? If there's enough internal heat to drive geysers, then it's not impossible that there could be a subsurface ocean lurking beneath the ice, hidden from view. And if an ocean exists, then that opens up all sorts of possibilities for life. Triton's history as a captured world means it didn't form in the same environment as Neptune's other moons. It started its life somewhere else, likely in the Kuiper Belt, meaning it could have been shaped by entirely different conditions before it ever became part of Neptune's system. If any microbial life had once existed on Triton before its capture, could it have survived the chaos of being yanked into a new orbit? Could there still be something beneath the ice, living in an ocean that has been locked away for eons? For now, Triton remains one of the most intriguing but unexplored places in the solar system. Voyager 2's brief flyby gave us just a glimpse, raising more questions than answers. No spacecraft has returned since, but there have been ideas. Missions proposed to study Triton in detail, searching for signs of an ocean, investigating its geysers, and unlocking the mystery of its bizarre orbit and geological activity. It remains a moon that defies expectations, behaving in ways that seem impossible for a world so far from the sun, reminding us that the strangest places in the solar system aren't always the ones we think they'll be. 8. The edge of the solar system, Kuiper Belt and Oort cloud, Sedna, and other rogue objects. Triton's story as a captured wanderer already blurs the lines between the familiar planets and the vast unknown, But it's not the only object with a history written in gravitational chaos. If anything, Triton's journey hints at something bigger lurking far beyond Neptune, a region where the sun's influence weakens and the rules of planetary order start to fall apart. This is where the solar system fades into the cosmic wilderness, where scattered worlds drift in eccentric orbits, untethered from the neat, predictable paths of the major planets. Some of these objects, like Pluto and Eris, at least have the dignity of belonging to the Kuiper Belt, but others are far more elusive, drifting so far out that they barely belong to the solar system at all. Among these, Sedna stands out, not just because of its bizarre orbit, but because of what it might be telling us about the hidden architecture of our own cosmic neighborhood. Sedna doesn't follow the usual pattern of planetary orbits. It doesn't loop around the sun in a predictable, circular path like Earth or Jupiter. Instead, it travels along a stretched-out, elongated orbit that takes it from relatively close, still far beyond Pluto, all the way into the distant unknown, nearly 1,000 times farther from the sun than Earth. It takes over 11,000 years to complete a single orbit, meaning the last time Sedna was anywhere near the inner solar system, human civilization hadn't even begun to form. Its trajectory makes no sense if you assume the planets are the only things affecting it. Something must have disturbed it long ago. Either a passing star, a massive unseen planet, or the lingering influence of the sun's birth cluster, when it formed in a crowded nursery of other stars that have long since drifted apart. But Sedna is only the beginning of the mystery. It's not alone. Other objects with similarly stretched out orbits, sometimes called detached objects, have been found, each one suggesting that the outer solar system isn't as empty as it once seemed. The problem is that these worlds are so far away, moving so slowly, that studying them is like trying to track a ghost. They hint at something larger pulling the strings, but whatever that might be remains unknown. Some theories suggest a massive, undiscovered planet, sometimes called Planet 9, lurking in the dark, its gravity gently nudging Sedna and others into these unusual orbits. Others propose a more chaotic past, where rogue planets or passing stars shaped the outer solar system into the scattered mess we see today. Beyond Sedna and its mysterious companions, there's the even more distant frontier, the Oort cloud, a vast, spherical shell of icy debris that marks the true edge of the solar system. Unlike the Kuiper Belt, which is relatively close and somewhat structured, the Oort cloud is a different kind of beast entirely. It's not a belt, but a cloud, stretching so far that its outer edges blend into the interstellar void. This is where the solar system's gravitational grip weakens to the point where a passing star, or even the faint tides of the Milky Way itself, can dislodge comets and send them plunging toward the inner solar system. The comets that occasionally light up our night skies, like Halley's Comet or Comet Neowise, likely began their lives in the Oort cloud, spending millions of years in deep freeze before some cosmic disturbance sent them inward on a long, looping journey toward the sun. The problem with the Oort cloud is that, for all its theoretical importance, no one has ever actually seen it. It exists as an idea, a necessary explanation for the origins of long-period comets, but direct observations are almost impossible. The objects out there are simply too small and too far away to be seen with current technology. All we have are indirect clues. Comets that appear suddenly from the abyss, orbital patterns that hint at a distant population of ice worlds, and models that predict its existence based on how the solar system formed. If it's real, and almost every piece of evidence suggests it is, then it represents a completely different kind of solar system than the one we're used to. It's not just planets and moons anymore. It's an entire hidden realm of frozen remnants, worlds that have never felt the warmth of the sun, drifting in a liminal space where the solar system ends and interstellar space begins. Somewhere out there, maybe in the Oort cloud, maybe even beyond it, rogue objects like Sedna or even entire planets could be hiding. These are worlds that don't play by the usual rules, orbiting in ways that suggest they were shaped by forces we don't yet understand. They don't fit into the neat categories of planets, moons, or asteroids. They're remnants of a different era, leftovers from the solar system's chaotic past, waiting in the cold for us to finally notice them. And with every new discovery, Every strange orbit, every distant world that doesn't quite fit. The mystery deepens, pulling us further into the unknown. The Oort cloud. If Sedna and its scattered companions hint at a hidden structure beyond the known planets, then the Oort cloud takes that idea and stretches it to its absolute limit. It isn't just a distant belt of ice and rock like the Kuiper Belt, nor is it a single, defined region with clear boundaries. Instead, it is a vast, almost incomprehensible shell of frozen debris that surrounds the solar system in every direction, a relic of the sun's earliest days that has been left to drift in deep space for billions of years. Unlike the planets and moons, which follow orderly orbits around the sun, the objects in the Oort cloud are scattered, slow-moving, and barely bound to the solar system at all. They exist in a gravitational limbo, feeling the sun's presence only faintly, their movements sometimes nudged by the subtle pull of passing stars or even the slight tidal forces of the Milky Way itself. The sheer scale of the Oort cloud makes it difficult to wrap one's head around. It begins somewhere beyond the Kuiper Belt, perhaps 1,000 times farther from the sun than Earth, but it doesn't stop there. It extends outward for light years, reaching a distance where the sun is just another star in the sky, no longer the dominant force that dictates motion the way it does in the inner solar system. If a spacecraft were to travel in that direction, it would take centuries to cross the cloud's full extent, and by the time it left, it would be drifting into true interstellar space, leaving the sun's influence behind entirely. It's a place so remote, so untouched, that nothing in human history has ever come close to reaching it. The farthest probes we've ever sent, like Voyager 1 and 2, won't even brush the inner edge of the Oort cloud for thousands of years, let alone escape it. What makes the Oort cloud so important isn't just its size or its remoteness, but what it contains. It's thought to be home to countless icy objects, some no bigger than mountains, others potentially as large as dwarf planets, all leftovers from the early solar system that never had a chance to form into something more significant. These frozen worlds have spent billions of years in cold storage, never feeling the warmth of the sun, never colliding or changing, preserved in time since the days when the planets were still taking shape. And every once in a while, something disturbs one of them. A passing star, a distant gravitational nudge, and sends it spiraling inward, falling toward the sun on a long, looping journey that can last thousands or even millions of years. These are the long-period comets, the ones that appear suddenly in the sky, blazing brightly as they heat up and shed trails of dust and gas. Unlike the short-period comets of the Kuiper Belt, which return predictably every few years or decades, these comets come from so far away that their orbits stretch beyond human history. When a comet like Hale-Bopp or Neowise appears, it's often the first time it has come close to the sun in millions of years, and by the time it leaves, it may never return in our lifetimes. Some of them fall into stable orbits, becoming recognizable visitors that appear once every few centuries, while others are slingshot away entirely, cast out of the solar system forever by a close pass with Jupiter or the Sun. The existence of the Oort cloud also raises a larger question about the solar system's formation. Where did these objects come from? The most accepted idea is that they were once part of the early solar system, forming closer in but getting thrown outward by the chaotic movements of the giant planets in their youth. Jupiter and Saturn, in particular, would have been gravitational wrecking balls in the solar system's early history, flinging smaller debris outward with such force that it never returned. Over time, these scattered remnants settled into a vast, spherical distribution, forming what we now call the Oort cloud. But there's also another possibility, one that suggests not all of these objects were born here. Some of them may have come from other stars entirely, ejected from their own solar systems and captured by the sun's gravity billions of years ago. If that's the case, then the Oort cloud isn't just a fossil of our own solar system. It could be a graveyard of interstellar debris, a collection of icy wanderers from different corners of the galaxy, frozen relics of worlds that never formed. Yet, for all its significance, the Oort cloud remains entirely unobserved. No telescope has ever imaged an object within it, and no spacecraft has ever come close to reaching it. Its existence is inferred, not seen, built from the indirect evidence of comets, and the mathematical models of solar system formation. But if we ever do reach it, if a future probe, centuries from now, drifts into its depths and sends back images of ancient, untouched worlds, it could be one of the last great frontiers of our own solar system. A place where time stands still, where the solar system meets the interstellar void, and where the frozen remains of cosmic history wait in the darkness, undisturbed for billions of years. Voyager 1 and 2. While the Oort cloud remains an unseen and untouched boundary between our solar system and the rest of the galaxy, there are two tiny machines that have already crossed into that vast unknown, carrying with them the story of a civilization that once looked up at the sky and wondered what lay beyond. Voyager 1 and 2, launched in 1977, were never meant to become interstellar travelers. Their mission was to explore the outer planets, Jupiter, Saturn, Uranus, and Neptune, sending back breathtaking images and groundbreaking data that reshaped our understanding of these distant worlds. But their journey didn't end there. Long after their primary mission was complete, they continued drifting outward, past the realm of planets, through the Kuiper Belt, and into the strange, turbulent edge of the sun's influence, a place where solar winds die out and the true emptiness of interstellar space begins. For years, they sailed through the heliosphere, the vast bubble of charged particles that the sun blows into space, gradually feeling the effects of its power weaken as they reached the boundary known as the heliopause. This was the true threshold, the point where the sun's presence fades and the influence of the galaxy takes over. Voyager 1 crossed that boundary first in 2012, officially becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018, confirming that they had both left the solar bubble behind and were now drifting through the unknown, still carrying out their final task of whispering back data from a place no spacecraft had ever gone before. What they found out there was unlike anything scientists had predicted. The space beyond the heliopause wasn't just an empty void, but a strange and turbulent region filled with cosmic radiation, interstellar plasma, and magnetic fields that twisted and fluctuated in ways we had never directly observed. The Voyagers, even in their old age, provided some of the only first-hand measurements of this uncharted territory, revealing that the boundary between our solar system and the rest of the galaxy is far more complex and dynamic than we once thought. And yet, for all their scientific achievements, there's something undeniably poetic about their journey. These tiny, battered machines, powered by decaying plutonium, still moving forward, still reaching into the unknown, still carrying a message from the planet that built them. Because beyond their instruments and cameras, beyond the decades of scientific data, each Voyager carries something unique, the Golden Record, a carefully curated collection of sounds, music, and images meant to serve as a snapshot of humanity, a message to any distant intelligence that might one day stumble across these silent wanderers. The crackling voice of Carl Sagan and his team selecting greetings in dozens of languages, the laughter of a baby, the sounds of the ocean, the beating of a human heart. These are the echoes of Earth, frozen in time, drifting endlessly through space. If the Voyagers outlive our civilization, if the world that created them fades into history, they will still be there, carrying that final story of a species that once dreamed of the stars. And they will outlive us. Barring an impossible stroke of luck, no alien civilization will ever find them, and no human will ever retrieve them. Long after their power sources fail and they fall silent, they will keep moving, drifting endlessly through the void, untouched by time or entropy. In 40,000 years, Voyager 1 will pass within 1.6 light-years of a star in the constellation Camelopardalis, and Voyager 2 will follow a similar path, wandering among the stars for millions, perhaps billions of years. Long after the sun has exhausted its fuel, long after the Earth itself has changed beyond recognition, these two tiny spacecraft will still be out there, carrying the last traces of a world that once sent them on their way. 9. Interstellar space and the nearest stars. Cosmic radiation and the challenges of deep space travel. And so the Voyagers drift further into the unknown, carrying their fragile cargo of human memory into the depths of interstellar space, a place where the rules of existence shift into something more hostile, more unrelenting, more alien than anything we've encountered before. Beyond the protective bubble of the sun's influence, space is not just emptiness. It is a battlefield of invisible forces, a place where radiation isn't just a background nuisance, but a constant, eroding presence, an ever-present reminder that deep space travel is not just about distance, but survival. Cosmic radiation is one of the biggest barriers to human exploration beyond our solar system. An invisible storm of high-energy particles moving at nearly the speed of light, ejected from supernovae, distant galaxies, and the violent processes that shape the universe itself. Within the sun's reach, the heliosphere provides some protection, a kind of natural force field that deflects many of these harmful particles. But out in true interstellar space, there is no such shield, no planetary atmosphere to absorb the damage, no magnetic field to redirect the onslaught. There is only raw exposure, and for anything biological, that means trouble. For a human crew venturing beyond the solar system, this radiation isn't just an abstract problem. It's a death sentence stretched over time. Constant exposure would damage DNA, increase cancer risks, weaken immune systems, and slowly degrade the body at a cellular level. The very structure of spacecraft would weaken over decades, metal becoming brittle under the relentless impact of high-energy cosmic rays. Electronics, the brain of any interstellar mission, would be at risk of data corruption and catastrophic failure. Shielding a crew from such radiation isn't as simple as adding a few layers of metal. In fact, traditional materials can sometimes make things worse by triggering secondary radiation effects as incoming particles smash into them, creating even more harmful byproducts. Some solutions have been proposed, ideas ranging from magnetic force fields mimicking Earth's defenses to thick walls of water or hydrogen-rich plastics that might absorb some of the incoming radiation. But the truth is, interstellar travel is a different beast entirely. A journey to even the nearest star, Proxima Centauri, would take thousands of years with current technology, meaning the challenge isn't just surviving the radiation, but surviving time itself. Any crew would need a generational ship, a self-sustaining world in its own right, capable of keeping people alive not just for years, but for lifetimes. And yet, even with all these obstacles, the dream persists. The idea that one day, we might step beyond the comforting reach of our sun, truly leaving home behind, to touch the light of another star. For now, our closest neighbors remain unreachable, their light just an echo of something tantalizingly close yet impossibly far. Proxima Centauri, the dim red dwarf that lies a mere 24 light-years away, remains the closest star to our own, a place where a potentially habitable exoplanet orbits within its feeble glow, its surface bathed in harsh solar flares that might sterilize any chance of life. Beyond it, Alpha Centauri A and B, a pair of sun-like stars locked in a slow gravitational dance, beckon with the promise of new worlds, new landscapes that we may never see. But this is the reality of interstellar space. It is vast, it is punishing, and it is indifferent to the fragile creatures that dare to dream of crossing it. And yet, the moment we stop dreaming of such things, we cease to be the species that sent the voyagers into the void, the species that built telescopes to peer into the beginning of time, the species that looked at the night sky and decided that the stories written in the stars were worth chasing, no matter how impossible they seemed. Alpha Centauri system. But for all the obstacles, for all the cold, empty space between us and the stars, there remains something undeniably alluring about the Alpha Centauri system. It isn't just the closest star system to our own. It is the first real glimpse we have into what might be possible beyond the reach of our sun. The three stars that make up this system, Alpha Centauri A, Alpha Centauri B, and the Lonely Wanderer, Proxima Centauri, exist as a reminder that not every distant light is just an unreachable point in the sky. Some are destinations, and one of them, Proxima Centauri B, holds a kind of promise that is difficult to ignore. Orbiting the small, dim red dwarf Proxima Centauri, this exoplanet is tantalizingly close in cosmic terms, just over 4 light-years away, but that distance is still a near impossible leap for anything traveling at human speeds. The most promising thing about it, however, is its location. A tight orbit around its parent star, sitting within what scientists call the habitable zone. This is the narrow band of space where, in theory, liquid water could exist, where the temperatures aren't too extreme to prevent the chemistry of life from taking root. It is, on paper, one of the best places we know of where the conditions might not just allow for life, but possibly even sustain it. But reality is rarely as simple as it seems. Proxima Centauri is not a quiet, stable sun like ours. It is a red dwarf, small and ancient, but prone to violent tantrums in the form of powerful stellar flares that send bursts of radiation across space, slamming into anything unfortunate enough to orbit nearby. Proxima Centauri b, despite its promising position, likely endures this onslaught on a regular basis, meaning any atmosphere it once had may have been slowly stripped away, leaving behind a barren, lifeless husk. Or maybe not. Maybe it has a magnetic field strong enough to hold on to whatever air it once possessed, shielding it just enough to keep the surface from being utterly sterilized. Maybe deep beneath a protective ice layer, or in some underground cavern, something still clings to existence, defying the odds in a place where no one expected to find anything at all. The frustrating thing is that we don't know. Proxima Centauri b is both close and impossibly distant, a place we can barely see, let alone study in detail. Future telescopes might change that, revealing whether its atmosphere is intact, whether signs of water exist, or even, if we're lucky, whether something biological has taken hold there. But for now, it remains a mystery, a world just out of reach, teasing us with the possibility that we are not alone, that even within the first few steps beyond our solar system, the conditions for life might already be waiting. And if that's the case, then what lies even further? How many other worlds are out there, orbiting their quiet, distant suns, waiting for us to look closely enough to see them for what they truly are? Theories of interstellar travel. If the nearest potentially habitable world sits only 4 light-years away and is still so unreachable with our current technology, then what does that say about the rest of the galaxy? The distances between stars are not just vast, they are crushingly, impossibly large on a human scale. Even the fastest spacecraft ever built, moving at speeds that defy everything we experience in daily life, would take thousands of years to cross the smallest fractions of this cosmic ocean. Yet, the idea of staying trapped within one tiny solar system forever is something that doesn't sit well with human nature. We have always been wanderers, always pushed past the horizon, and now the greatest horizon of all looms ahead, daring us to find a way to cross it. The problem is that conventional physics makes interstellar travel a nightmare. No spaceship, no matter how advanced, can just go fast in the way people imagine. Rockets burn fuel, and the more fuel they carry, the heavier they become, which means they need even more fuel to move. It's a vicious cycle, a frustrating reminder that the laws of physics don't bend easily to ambition. But that hasn't stopped us from imagining ways to cheat those laws, ways to sidestep the harsh reality of space in favor of something that might just make the impossible possible. Warp drives, for instance, sound like pure science fiction, yet they are one of the most theoretically promising ideas ever conceived. Instead of moving a ship forward at impossible speeds, a warp drive bends space itself, compressing the space in front of the ship and expanding it behind. The ship itself never technically moves faster than light. It simply rides a wave of distorted space-time, avoiding all the problems that come with breaking the cosmic speed limit. The concept isn't just a fantasy. The equations work, at least in theory. The issue is that to make it happen, the energy requirements are so enormous that they border on magic. The amount of exotic matter, something we aren't even sure exists, needed to power such a drive would be astronomical, making the dream of warp travel one that remains firmly in the realm of speculation. For those unwilling to bet on bending the very fabric of reality, there is the far less glamorous idea of generation ships. If we can't cheat the speed limit, then why not accept the long journey for what it is? Instead of trying to get to another star within a human lifetime, we build self-sustaining ships designed to carry entire civilizations. Whole generations would be born, live, and die aboard these massive arcs, never knowing anything but the artificial world of their starship, all in the hope that their distant descendants would one day arrive at a new home. It's a plan that sounds almost reasonable until you consider the sheer complexity of keeping human society stable for thousands of years inside an enclosed, isolated world where resources are finite, and any small failure could doom the entire mission before it ever reaches its destination. The psychological and cultural challenges of generation ships might be even harder to solve than the technological ones. Then there's the idea of simply sleeping through the journey, a concept that has appeared in fiction so many times it feels inevitable that we will one day make it a reality. Cryosleep, suspended animation, or some form of deep hibernation could allow travelers to endure the long trip without experiencing the time that passes, waking up as if no time had gone by at all. The problem is that freezing a human body, keeping it alive in a state of near death for centuries, and then reviving it without damage is something we have no real way of doing yet. Lower animals like frogs and certain fish can survive being frozen solid, their bodies adapting to the ice in ways that prevent cellular damage. But humans are far more complex, and we simply aren't built for that kind of dormancy. Artificially induced hibernation is being studied, but the leap from putting someone into a controlled metabolic slowdown for a few weeks to keeping them in stasis for hundreds of years is still a vast and uncertain one. The truth is that interstellar travel, no matter which way we approach it, remains a distant dream, one held back not just by technological limitations, but by the fundamental laws of the universe itself. Every idea we have, whether it's bending space, building massive self-sustaining ships, or figuring out how to sleep through the centuries, comes with challenges so extreme that none of them seem feasible in the immediate future. And yet, the fact that we keep trying to figure it out, that we refuse to accept the idea of being trapped in this one small corner of the galaxy, says something about what it means to be human. Whether it's in 100 years or 1,000, whether it's through a breakthrough we can't yet imagine or simply through sheer determination, there is a feeling that one day, someone will take that first impossible step beyond the solar system and never look back. 10. The Milky Way Galaxy. Structure of the galaxy. Even if we find a way to cross the enormous gulfs of space, even if we manage to break free from the gravity well of our tiny solar system and set course for the stars, we would still be nowhere near reaching the true edges of our cosmic home. Because as vast as interstellar distances may seem, they are nothing compared to the scale of the Milky Way itself. Our galaxy is not just a collection of stars. It is an immense, rotating structure of unimaginable complexity, a gravitationally bound spiral of gas, dust, and dark matter stretching across more than 100,000 light-years. It is ancient, older than the Earth itself, older than the Sun, a system that has been forming, reforming, and consuming itself for billions of years, long before humans ever had the arrogance to look up at the sky and think they could understand it. From where we sit, tucked away in one of the quieter corners of the Milky Way, the true nature of our galaxy isn't immediately obvious. The night sky gives us only the faintest hints of its grandeur, a dense strip of stars cutting across the darkness, a reminder that we are inside something far larger than we can comprehend. But if we could step back and look at it from the outside, we would see a vast pinwheel of stars, a rotating disk with curved, spiraling arms filled with stellar nurseries, dying suns, and planets beyond counting. These spiral arms, where new stars are constantly being born, are the places where the action happens, where gravity pulls clouds of gas together, condensing them into blazing spheres of fusion. Our own sun, along with everything we know, sits in one of these arms. The Orion Arm, just a minor branch of a much grander structure. Toward the center, things are different. The galactic core is a chaotic, crowded place, dense with ancient stars packed so closely together that the sky would be ablaze with light. At its heart lies something far more ominous. Sagittarius A*, a supermassive black hole, millions of times the mass of our Sun, a gravitational abyss around which the entire galaxy orbits. It is a monster that has shaped the very structure of the Milky Way, warping space-time itself, consuming anything unfortunate enough to drift too close, yet somehow existing in a perfect balance with the chaos surrounding it. This singularity, this immense concentration of mass, is not just a curiosity. It is an integral part of the galaxy's existence, anchoring the spiral, ensuring that the Milky Way continues to hold together over the course of cosmic history. But despite its spiraling beauty, despite its glowing arms and dense core, most of the Milky Way is something we cannot even see. The visible matter, the stars, the planets, the glowing nebulae, makes up only a small fraction of the galaxy's true mass. The rest is dark matter, an invisible, enigmatic substance that refuses to interact with light, detectable only through its gravitational influence. Without it, the Milky Way would not be able to maintain its shape. Its stars would drift apart, its structure would collapse, and its delicate balance would be lost. And yet, for all its importance, we still do not know what dark matter truly is, only that it holds our galaxy together like some unseen glue, keeping the grand cosmic spiral intact. For all our attempts to understand the Milky Way, we remain nothing more than temporary guests, tiny inhabitants of a single, unremarkable star system in one of billions of galaxies scattered throughout the universe. And even if one day we find a way to leave this home behind, to step beyond the familiar spiral arms and set out across the endless void, the simple truth remains: we will never truly escape it. Because no matter how far we go, no matter how many light years we travel, we will always be a part of the Milky Way, forever bound to its motion, its history, and its quiet, indifferent existence. Black holes, Sagittarius A, event horizon and spaghettification. And at the heart of it all, lurking in the dense chaos of the Milky Way's core, is the one thing that defies understanding: a void in space where even the laws of physics collapse into something unrecognizable. Sagittarius A asterisk, the supermassive black hole anchoring our galaxy, is not simply a place, but an absence, a gravitational well so deep that not even light can escape. It is a reminder that, despite all we think we know, there are forces in the universe that exist beyond our ability to truly comprehend, phenomena that stretch the very meaning of existence to its breaking point. Black holes are, in a way, the ultimate paradox. They are born from the death of the most massive stars, yet they are among the most powerful forces shaping the cosmos. They are objects, yet they are also empty space, regions where matter is crushed into oblivion by its own weight. The event horizon, the invisible boundary separating what falls in from what can still escape, is not a surface or a physical barrier but a one-way threshold, a point where reality itself becomes distorted beyond recognition. To an outside observer, anything approaching a black hole appears to slow down, as if frozen in time, while from the perspective of the falling object, the universe itself stretches and warps into a surreal nightmare of infinite distortion. And then there's spaghettification, a word that sounds comical until you realize what it actually means. A black hole's gravitational pull is not uniform. It is stronger the closer you get. If you were to fall in feet first, the gravity at your feet would be immensely stronger than the gravity at your head, stretching your body like a strand of pasta, pulling atoms apart with a force so absolute that even subatomic particles would be torn from one another. There is no coming back from this. No rescue, no last-minute escape, just an endless descent into darkness, where space itself is bent and time ceases to hold meaning. Yet, for all their destructive potential, black holes are not simply cosmic monsters devouring everything in their path. They shape galaxies, influence the orbits of stars, and act as engines of cosmic evolution. Some black holes, when surrounded by enough material, become active galactic nuclei, spewing radiation and jets of particles across light years, illuminating the universe in spectacular, violent displays of energy. And despite their reputation as inescapable voids, black holes are not truly eternal. Over unimaginable timescales, they slowly evaporate through Hawking radiation, losing energy particle by particle, until, in the distant future, they may simply fade away into nothingness. But what happens inside? What lies beyond the event horizon, where all information is lost, where the known universe ceases to function? No one knows. General relativity suggests an infinitely dense singularity at the core, a point where physics itself breaks down, but quantum mechanics refuses to accept this answer. Somewhere in the collision of these two great theories, the true nature of black holes remains hidden, locked away behind the very fabric of space and time. Maybe they are tunnels to other universes. Maybe they contain remnants of crushed realities. Or maybe they are simply the universe's way of keeping its deepest secrets from ever being known. Whatever they are, they remain among the most mysterious and fascinating enigmas in existence, silent and indifferent, waiting in the darkness at the heart of it all. Exoplanet discoveries. But black holes, for all their mind-bending strangeness, are not the only mysteries lurking in the vastness of space. As technology has improved and telescopes have peered deeper into the cosmos, a different kind of discovery has reshaped our understanding of the universe. Not the terrifying voids of collapsed stars, but distant worlds orbiting alien suns, planets that might, just might, be capable of harboring life. The search for exoplanets has become one of the most exciting frontiers of modern astronomy, a relentless hunt for worlds beyond our solar system that has revealed just how small and ordinary our own little corner of the cosmos really is. It was the Kepler Space Telescope that changed everything. Before its launch, the idea of planets beyond our solar system was mostly theoretical, with only a handful of discoveries to suggest they were even common. But Kepler, staring unblinking at a single patch of sky, revolutionized our understanding. It revealed that planets are not just abundant, but everywhere, far outnumbering the stars themselves. Some orbit too close to their stars, locked in infernos of heat and radiation, while others drift too far, frozen wastelands doomed to eternal night. And then there are those in the habitable zone, that narrow region where conditions might allow for liquid water, where life, at least as we know it, could possibly take hold. Among the most intriguing of these discoveries are the so-called super-Earths, planets larger than our own but smaller than Neptune, straddling the line between rocky worlds and gas giants. Some may have thick atmospheres, others vast oceans stretching across their entire surfaces, and a few, just maybe, could be eerily similar to Earth. But here's the strange thing. Our own solar system has nothing like them. The absence of a super-Earth in our backyard only makes their presence elsewhere more fascinating, forcing scientists to reconsider what planetary formation really looks like and whether Earth is truly as ordinary as we once assumed. And yet, for all the data, for all the distant light curves hinting at unseen worlds, we are still left with one pressing question: what is actually out there? The numbers tell us that billions of planets should exist in habitable zones, that some should have conditions ripe for life, but numbers are not proof. They are only the whisper of possibility, a promise that somewhere, hidden among the stars, another Earth might be waiting to be found. And with newer telescopes, more advanced sensors, and the first real glimpses at distant atmospheres, that search is only just beginning. Future of the Milky Way. But finding new worlds and imagining their possibilities is only a small part of the bigger picture, because the universe doesn't just sit still and wait for us to figure it out. Everything is in motion, shifting, colliding, merging, and reshaping itself in ways that stretch across incomprehensible spans of time. Even our own galaxy, the familiar swirl of the Milky Way, is not some eternal and unchanging thing. It has a future, and that future is hurtling toward a collision on a scale so massive it's almost impossible to visualize. Andromeda, the nearest spiral galaxy to our own, is not just a distant neighbor. It's on a collision course with us. Right now, it's over 2 million light-years away, but it's moving toward the Milky Way at around 110 kilometers per second. That might sound impossibly fast, but in the vast emptiness of intergalactic space, it still takes billions of years for galaxies to meet. The fate of the Milky Way is already written in gravitational equations, an inevitable consequence of cosmic motion. In about 4.5 billion years, the two galaxies will finally collide, their vast arms stretching and distorting, flinging stars into new orbits, warping gas clouds into strange shapes, and setting off a spectacular burst of star formation as their interstellar materials mix. Despite the apocalyptic sound of a galactic collision, the reality is surprisingly gentle. Galaxies are mostly empty space, vast collections of stars separated by unfathomable distances. When Andromeda and the Milky Way merge, it won't be like two solid objects smashing together. Instead, their stars will pass through one another like ghosts, rarely colliding directly. But the gravitational chaos will completely change the structure of both galaxies, twisting them into tidal tails, stretching and compressing them until they begin to settle into something new. A massive elliptical galaxy, sometimes called Milkomeda. As for Earth, by the time this happens, our own planet may already be unrecognizable. The sun will have grown hotter, making life on the surface increasingly difficult, if not impossible. If any distant descendants of humanity are still around, they may be looking at the cosmic dance from a different home, watching as the sky fills with new patterns of stars, reshaped by the slow-motion catastrophe unfolding on an unimaginable scale. And while this collision will be dramatic, it won't be the last. Because the universe is always in motion, and even the most stable things are only temporary. 11. The universe beyond. The local group of galaxies. And even after the Milky Way and Andromeda have settled into their new identity as one giant elliptical galaxy, they will still be just a small part of something larger. The Milky Way is not alone, not even in the grand sense of sharing the universe with countless galaxies. It belongs to a tight-knit neighborhood known as the local group, a cosmic family bound together by gravity, moving as a collective through the vastness of space. At the heart of this small galactic cluster are the Milky Way and Andromeda, the two dominant members whose inevitable collision will redefine their structure. But surrounding them are dozens of smaller galaxies, some of them little more than faint smudges of stars held together by dark matter, while others, like the large and small Magellanic Clouds, shine brightly in the night sky of the southern hemisphere. These two irregular galaxies orbit the Milky Way like wayward satellites, slowly being stripped apart by its gravitational pull. Streams of gas stretch between them and our galaxy, remnants of their slow-motion struggle against the force that will eventually consume them. The local group isn't an isolated collection, either. It's just one small part of something even bigger. The Virgo supercluster, an enormous structure of hundreds of galaxies stretching across millions of light years. Within that, the local group is like a minor suburb in an endless cosmic metropolis, constantly shifting as galaxies move, merge, and evolve. The boundaries between these groups aren't rigid, and gravity constantly tugs at their edges, creating a slow but relentless drift towards something even larger. Despite the enormous distances between them, the galaxies in the local group are deeply connected, their interactions shaping their futures. Some are being pulled apart, their stars gradually absorbed into the larger galaxies. Others, like Andromeda, are on collision courses that will reshape the local cosmic landscape entirely. The Milky Way and its companions may seem stable and familiar now, but nothing in the universe is permanent. Over billions of years, these galaxies will continue their slow dance, merging, colliding, and dispersing, their fates intertwined in a gravitational ballet that stretches across time itself. The Virgo supercluster. But the local group, despite its significance to us, is just a minor thread in a much larger cosmic web. It belongs to something far greater, a vast congregation of galaxies known as the Virgo supercluster, a sprawling collection of over 100 galaxy groups and clusters, all loosely bound together by the relentless pull of gravity. Unlike the cozy familiarity of our own Milky Way and its nearest neighbors, the Virgo supercluster is an enormous, chaotic expanse where galaxies move in complex patterns, drawn toward unseen forces, colliding, merging, and stretching across distances so vast that even light itself takes millions of years to travel between its most distant members. At the heart of it all lies the Virgo cluster, a dense, gravitational hub of thousands of galaxies, each one teeming with billions of stars, planets, and possibly civilizations that may never know of our existence. This cluster acts as a kind of cosmic anchor, exerting a gravitational influence over everything in the supercluster, pulling galaxies toward it in a slow but inevitable journey that has been unfolding for billions of years. The local group, including the Milky Way and Andromeda, is not immune to this pull. We, too, are drifting toward the Virgo cluster, caught in the flow of a grander motion that we have no power to resist. But even the Virgo supercluster is not the end of the story. It is not an isolated entity, floating alone in an empty universe. Instead, it is just one part of an even larger structure, something so vast and intricate that it challenges our very perception of scale. It belongs to the Laniakea supercluster, an even greater network of galaxies that extends across hundreds of millions of light years, a structure so immense that it was only recently identified as a single, interconnected system. Within this supercluster, the galaxies are not merely scattered randomly. They form filaments and tendrils, strands of cosmic matter stretched out like the threads of an impossibly vast web. Everything within the Virgo supercluster, including our own tiny place in it, is moving, shifting, drawn toward regions of higher gravitational concentration in an endless cosmic migration. And beyond even that, the universe continues, stretching outward in all directions, filled with billions of other superclusters, each one its own vast and unknowable realm. The more we learn, the more we realize that our place in the cosmos, no matter how grand it may seem, is just a tiny part of an unfathomable whole. The cosmic web. But even the Virgo supercluster and the larger Laniakea supercluster, despite their mind-bending scale, are just fragments of something even grander, an arrangement of matter that stretches across the universe in a way that is almost incomprehensible. Galaxies are not scattered randomly through space, nor are superclusters floating alone like isolated islands. Instead, everything follows a deeper structure, an intricate, web-like arrangement of matter that spans billions of light years. This is the cosmic web, a vast, filamentary network where galaxies, clusters, and superclusters are strung together in long, delicate threads of matter, weaving through the void in patterns that look almost biological, as if the entire universe were the nervous system of some unimaginable, ancient being. These filaments, each one containing countless galaxies, are the result of gravity sculpting the cosmos over billions of years. Matter did not distribute itself evenly after the Big Bang. Tiny quantum fluctuations in the early universe created denser regions that gradually pulled more and more material toward them, forming strands of dark matter and hydrogen gas. Over time, these strands thickened and galaxies took shape within them, lighting up the darkness in clusters along these invisible bridges. And between these glowing filaments lie vast, empty voids, deserts of space where galaxies are scarce, where the only thing stretching for millions of light years is a near-total absence of matter. Some of these filaments are so long that they span hundreds of millions of light years, linking together entire superclusters like threads tying together the fabric of the cosmos. They are not static, either. Over immense periods of time, they move, shift, stretch, and sometimes collapse into larger structures. The galaxies within them are not stationary either. Everything is being pulled, slowly but inevitably, toward regions of even greater mass. Toward massive gravitational sinks like the Great Attractor, a mysterious, unseen force that is dragging entire galactic superclusters toward it, including our own. At its largest scale, the cosmic web is a paradox. It is both staggeringly vast and eerily familiar, echoing patterns found in the most fundamental aspects of nature. From the filaments of neural networks to the way rivers carve their paths across a planet's surface. It suggests that the universe follows some hidden, universal law of structure, a pattern that repeats itself from the smallest microscopic scales to the largest expanses of existence. And yet, despite all our advances in understanding, we have only just begun to map it, to see its true shape and scope. Beyond what we can observe, it extends, stretching into the unknown, a reminder that no matter how much we uncover, the universe will always remain larger, more intricate, and more mysterious than we can ever fully comprehend. 12. The edge of the observable universe. Cosmic microwave background. The oldest light. But even the immense structure of the cosmic web, with all its filaments and voids, is just a small piece of what we can perceive. There is a limit to our vision, a boundary beyond which the universe remains hidden, not because there is nothing there, but because light itself has not had enough time to reach us. This edge of the observable universe is not a physical wall, but a horizon, a limit imposed by the age of the universe and the speed of light. The farther we look, the further back in time we see, until we reach a moment so ancient, so fundamental, that it marks the very first light to ever travel freely through space. The cosmic microwave background. This light, stretched and cooled over billions of years, is the faint afterglow of the Big Bang, a whisper from a time when the universe was unrecognizable. In its earliest moments, everything was a dense, hot plasma, an opaque fog of charged particles where light could not move freely. Photons were constantly colliding with electrons, scattered and absorbed before they could travel any meaningful distance. But then, something changed. Around 380,000 years after the Big Bang, the universe expanded and cooled enough for these charged particles to combine into neutral atoms, a process known as recombination. In an instant, space became transparent, and the trapped light was finally released, free to travel forever in all directions. This was the moment the cosmic microwave background was born, an imprint of the young universe frozen in time. What we see today is not the same brilliant flash that was once released, but its stretched out, redshifted remnants, cooled to just a few degrees above absolute zero. It fills the sky, an almost perfect uniform glow, but not entirely. Tiny fluctuations, subtle differences in temperature and density, are scattered throughout, the seeds from which galaxies and stars would eventually grow. These minuscule variations, mapped in stunning detail by telescopes like COBE, WMAP, and Planck, reveal the earliest scars of structure, a blueprint of everything that would come after. Without them, there would be no cosmic web, no galaxies, no planets, no life. And yet, the cosmic microwave background is more than just an image of the past. It is also a limit, a barrier we cannot see beyond. It marks the moment when light was freed, but before that moment, there was still a universe, one we cannot observe directly. What came before remains hidden, locked behind the fog of the early cosmos, a mystery still waiting to be unraveled. Scientists theorize about what might have happened in those first fractions of a second. The era of inflation, the birth of fundamental forces, the possible echoes of universes beyond our own. But the truth remains elusive. The cosmic microwave background is the oldest light we will ever see, a final glimpse before everything fades into the unknowable past, leaving us to wonder what lies beyond. Dark matter and dark energy, the invisible forces shaping the cosmos. But even as the cosmic microwave background gives us a glimpse into the universe's infancy, it also leaves us with unsettling questions. The familiar matter that forms stars, galaxies, and planets, everything we can see and touch, makes up only a small fraction of the cosmos. The rest remains unseen, detectable only by its influence on the universe itself. There is something else, something vast and invisible, shaping the very fabric of reality in ways we are only beginning to understand. Dark matter is the first of these hidden forces, an enigma that has haunted physics for decades. We cannot see it, nor does it emit or absorb light, yet it outweighs everything we do see by nearly 5 to 1. Its presence is revealed in the way galaxies spin, in the way light bends around invisible masses, in the way cosmic structures form and hold together. Without dark matter, galaxies would fly apart, unable to hold themselves together against the centrifugal force of their own rotation. Something must be there, something massive and yet undetectable, binding the universe together like an unseen scaffolding. The leading theories suggest it might be made of some unknown particle, one that barely interacts with normal matter except through gravity, but despite decades of searching, every attempt to detect it directly has failed. It is everywhere, surrounding us, passing through us, yet it remains untouchable. And if dark matter is the silent architect of the universe's structure, dark energy is the force that threatens to tear it all apart. Unlike dark matter, which holds things together, dark energy pushes them away, accelerating the expansion of the universe at an ever-increasing rate. This discovery was as shocking as it was accidental. Scientists had expected gravity to slow the expansion over time, yet when distant supernovae were observed in the 1990s, they revealed something entirely different. Instead of decelerating, the universe was speeding up, as if some unseen force was stretching space itself apart. What dark energy actually is remains a mystery. Some think it is a property of space itself, an inherent energy that grows as the universe expands, a modern resurrection of Einstein's once dismissed cosmological constant. Others suggest it could be something far stranger, a dynamic energy field that shifts and evolves over time, or even a sign that our understanding of gravity is fundamentally incomplete. Whatever it is, it dominates the cosmos, making up nearly 70% of everything that exists, yet it remains one of the greatest unknowns in physics. Together, dark matter and dark energy govern the universe in ways we can barely comprehend. One builds, the other pulls apart. One holds galaxies together, the other drives them away from each other. They are invisible forces that shape the destiny of the cosmos, dictating whether it will expand forever, rip itself apart, or collapse back into itself. We exist in the delicate balance between these two unknowns, in a universe where the vast majority of what exists is something we cannot even see. The more we uncover, the more we realize how much remains hidden, and as we look deeper into the cosmos, we are left with the unsettling truth that most of reality is still a mystery waiting to be solved. Theories on the universe's fate. If dark matter binds the universe together and dark energy tears it apart, then the ultimate question is not just what they are, but what they mean for the future. The universe is not static. It is changing, expanding, evolving, and the fate of everything. The galaxies, the stars, the atoms, the very concept of time itself, depends on which force ultimately wins. If gravity, anchored by dark matter, manages to hold its ground, the cosmos may collapse back into itself. If dark energy continues to accelerate the expansion, the universe may be stretched beyond recognition. The outcome is uncertain, but the possibilities are nothing short of terrifying. One potential fate is the so-called Big Freeze, a slow and inevitable march toward darkness and entropy. If the expansion of the universe continues indefinitely, then over unimaginable timescales, galaxies will drift farther apart, stars will burn through their fuel and die, and no new ones will be born. The universe will grow colder as energy becomes more and more spread out, and eventually, all that will remain are the remnants of stars, dead planets, and black holes slowly evaporating into nothingness. It is a death not by violence, but by exhaustion, a slow fading of everything until there is no usable energy left, just a frozen void stretching into eternity. A more violent and chaotic end could come in the form of the Big Rip, where dark energy does not simply push galaxies apart, but accelerates its expansion to an extreme, shredding everything in existence. In this scenario, the rate of expansion does not remain constant. It increases, and as it does, it begins to overcome not just the gravity holding galaxies together, but the very forces that hold atoms themselves intact. First, galaxy clusters will separate. Then, individual galaxies will unravel. As time passes, even solar systems will be torn apart, followed by planets, molecules, and finally, the very fabric of space itself will be ripped to shreds in one final, catastrophic moment. If dark energy behaves in this way, then the universe does not slowly fade into the cold. It is violently shredded apart, reduced to individual particles scattered across an ever-expanding abyss. And yet, there is another possibility, a fate that leads not to expansion, but collapse. The Big Crunch suggests that dark energy may not be the dominant force forever, and that at some point in the future, gravity might reclaim its throne. If the expansion of the universe slows and eventually reverses, then everything will begin to contract rather than expand. Galaxies will move closer, then collide, then merge into one colossal mass. Temperatures will rise, stars will reignite in a cosmic blaze, and as the contraction accelerates, everything will be pulled into a final catastrophic collapse. Space will shrink, time will slow, and all matter and energy will be crushed into an incomprehensibly dense point, possibly a return to the very singularity from which the universe was born. Some speculate that this could be a cycle, that a new universe might emerge from the wreckage, repeating the process over and over, an eternal cosmic rebirth with no beginning and no final end. The true fate of the universe remains uncertain, hidden in equations we are still struggling to solve and in forces we barely understand. We exist in a brief moment, a fragile window of time where stars still shine and galaxies still spiral, but the universe does not care for permanence. Everything we know is temporary. Every structure will eventually collapse, and whether the cosmos ends in a whisper, a scream, or a rebirth, it is a reminder that nothing lasts forever, not even the universe itself. Multiverse theory. If the universe itself is doomed to either expand into an empty void, collapse into itself, or be torn apart at the seams, then perhaps the most unsettling question isn't how it will end, but whether it's the only one. The idea that this universe, the one with its galaxies, its black holes, its stars, and its laws of physics, is all there is might be nothing more than a comforting illusion. Because if reality is as vast and unknowable as it seems, then why should there be just one universe? The multiverse theory suggests that what we call the universe is merely a tiny fragment of an infinitely larger reality, one in which other universes, perhaps an infinite number of them, exist beyond the reach of anything we can perceive. Some might be nearly identical to ours, differing by only the smallest details. Others could be incomprehensibly alien, governed by entirely different laws of physics, where even the fundamental forces that shape reality might not behave in any familiar way. One version of the multiverse theory comes from quantum mechanics, the strange and counterintuitive world where particles can exist in multiple states at once until observed. Some interpretations suggest that every quantum event that could happen does happen, but in different branches of reality. This means that every time a choice is made, a new universe splits off, one where things went one way and another where they went differently. Somewhere out there, another version of you exists, living a life shaped by a different set of choices, existing in a world where history unfolded in a completely different direction. Perhaps in one universe, life never emerged on Earth. In another, civilizations more advanced than we can imagine have already spread across the stars. In yet another, the constants of physics are just slightly different, making it a place where matter as we know it can't even exist. Another possibility arises from cosmic inflation, the idea that after the Big Bang, space expanded at an exponential rate, creating separate regions that became entirely disconnected from each other. If this process happens infinitely, then new universes could be forming all the time, each with their own properties, their own physical laws, and their own possibilities. Some of these universes might resemble ours. Others might be so different that the word universe hardly even applies, more like fragmented realities floating in a larger, unknowable space. Then there's the idea that universes might exist in higher dimensions, stacked on top of each other like pages in a book, separated by barriers we can't perceive. These universes might be closer to us than we realize, only a fraction of a millimeter away in another dimension, but forever inaccessible unless some unknown force or technology finds a way to bridge the gap. Some have even speculated that black holes might be gateways, leading not to singularities of infinite density, but to entirely different universes, each with their own beginning, their own expansion, and their own eventual fate. If the multiverse is real, then the implications are staggering. It means that everything we know, our history, our physics, our very concept of existence, might be nothing more than a localized phenomenon, an accidental arrangement of reality among countless others. It also raises questions we may never answer. Are these other universes connected? Can anything travel between them? Is there a deeper structure, an ultimate reality that contains them all? And perhaps the most haunting question of all, if there are infinite universes, then what does that mean for us? Are we unique, or just one version of an infinite set of possibilities? doomed to repeat ourselves over and over in countless variations? The universe was already vast beyond comprehension. The multiverse makes it infinite in ways we may never be able to grasp. If the multiverse is real, then our understanding of reality itself is incomplete, a mere sliver of something far greater than we could ever experience. But even if there is only one universe, the one we know, it is still so vast, so intricate, and so impossibly complex that it might as well be infinite. We began this journey standing on Earth, a small rocky planet orbiting an average star in a galaxy among billions, wondering where we fit into it all. And as we pushed outward, past the familiar planets of our solar system, beyond the icy debris of the Oort cloud, through the interstellar void and into the crowded city of the Milky Way, our perspective grew. We saw black holes lurking in the shadows, exoplanets dancing around distant suns, galaxies colliding, cosmic structures stretching across incomprehensible distances. We reached the very edge of what we could see, gazed at the first light of the universe itself, and still, we barely understood anything at all. The sheer scale of the cosmos is something the human brain was never built to fully grasp. We measure our lives in decades, our history in centuries, our civilizations in millennia, but the universe plays by a different set of rules, one where time is counted in billions of years and distances are so vast that even light, the fastest thing in existence, takes eons to travel between stars. And yet, despite how impossibly small we are, despite how little time we have compared to the grand lifespan of the cosmos, we have already begun to reach for something more. We have sent probes beyond our solar system, pointed telescopes into the depths of space, discovered planets where life might exist, and imagined futures where we might not just observe the universe, but take part in it. The dream of space colonization, of humans living on Mars or venturing beyond, no longer feels like pure fiction, but an inevitability waiting for us to figure out how. The search for extraterrestrial life continues, and though we have found no definitive proof, the mere possibility that we might one day hear a signal from an intelligent species is enough to change everything. There is something profoundly human about all of this. Our endless need to explore, to understand, to find meaning in the vastness that surrounds us. Every discovery, every probe sent to another world, every exoplanet found in a distant solar system is another step forward, another small piece of the puzzle falling into place. But even with everything we've learned, one question remains. Where do we go from here? Do we continue to explore, pushing further into the unknown until we are no longer just observers, but participants in the grand story of the universe? Do we reach a point where we must choose between staying confined to this one fragile planet or taking the risk of becoming a spacefaring species? And if we do go, if we spread across the stars and make the universe our home, what does that make us? Are we the first of our kind, or are we simply following in the footsteps of civilizations long gone? Perhaps there is no final answer, no ultimate destination. Maybe the universe is not something to be conquered or fully understood, but simply experienced. Maybe the real journey isn't about reaching the end, but about never stopping, never ceasing to wonder, never losing that part of us that looks up at the night sky and asks, "What's out there?" Because in the end, it's not just about where we are in the universe. It's about where we are going. And so, here we are, standing at the edge of everything. The observable universe, the limits of what we can see, what we can measure, what we can even begin to comprehend. From the familiar blues of Earth to the cold, silent void beyond the last whisper of starlight, we've traveled through time and space, diving into cosmic mysteries that stretch far beyond our little corner of the galaxy. But the journey doesn't really end here, does it? Because space isn't just something out there. It's a story still being written, with new chapters unfolding every day. New planets waiting to be discovered, new theories waiting to be tested, new questions waiting to haunt our sleepless nights. Maybe one day, someone watching this will be part of that next leap, colonizing Mars, mining asteroids, or even pushing past the boundaries of interstellar travel. Who knows? The universe is big enough to dream. If you made it this far, you're clearly the kind of person who loves the unknown, the kind who wonders about what's just beyond the horizon. So why stop here? There's more to explore, more to question, more late-night deep dives into the infinite. If you enjoyed this journey, give this video a like. It helps fuel future expeditions. And if you want more cosmic adventures, subscribe to Quiet Universe and join me as we continue unraveling the mysteries of existence, one strange and fascinating topic at a time. Until next time, keep looking up.